On December 15th, 2025, just weeks from now, an object from beyond our solar system will reach its closest point to Earth in recorded history. This isn't your typical space rock story. This is about 3I Atlas, the third confirmed interstellar visitor we've ever detected, and it's carrying secrets that have astronomers quietly debating behind closed doors. At 1.8 astronomical units away, roughly 170 million miles, 3I Atlas will pass closer to our planet than any confirmed interstellar object before it. But distance isn't what makes this moment significant. What matters is what we've discovered about this visitor during the 6 months we've been tracking its approach, and what those discoveries might mean for our understanding of what's really out there between the stars. If you're here because you want the full story, the data that doesn't make it into mainstream headlines, then stay with me. Hit that subscribe button and ring the notification bell, because what we're about to explore challenges everything we thought we knew about objects from other star systems. Drop a comment and tell me where you're watching from, and whether you think we're prepared for what December 15th might reveal. Let me start with something that should make you pause. 3I Atlas weighs at least 33 billion tons. That number comes from careful analysis of its trajectory, specifically from what it's not doing. When comets approach the Sun, they typically show what astronomers call non-gravitational acceleration. Ice sublimates from their surface, creating jets of gas that act like tiny rocket engines, nudging the object off its purely gravitational path. 3I Atlas shows almost none of this behaviour. Despite clear evidence that it's actively releasing gas and dust, its trajectory follows gravitational predictions with extraordinary precision. The only explanation that fits the observations is mass. Enormous mass. So much mass that the thrust from outgassing can't move it measurably. It's like trying to push an aircraft carrier with a garden hose. Here's where it gets interesting. If you assume 3I Atlas has the density of a typical comet, somewhere between rock and ice, that 33 billion ton mass translates to a diameter of more than 5 kilometers. That makes it thousands of times more massive than the previous interstellar visitors, Oumuamua and Borisov. Thousands of times. This creates what researchers call the mass budget problem. Based on our understanding of planetary formation and how much rocky material gets ejected into interstellar space, objects this large should be extraordinarily rare. We're talking about encountering something this massive perhaps once every 1,000 years, maybe longer. Yet here we are, barely a decade into systematic searches for interstellar objects, and we've found one of the rarest size classes possible. The statistics alone are troubling enough, but they're just the beginning. Let's talk about 3I Atlas's trajectory, because this is where coincidence starts looking less like chance and more like design. Our solar system is relatively flat. The 8 planets orbit the Sun in roughly the same plane, like dinner plates stacked at slightly different heights. This plane, called the ecliptic, reflects the geometry of the rotating disk of gas and dust from which everything formed billions of years ago. Interstellar objects shouldn't care about our ecliptic plane. They come from other star systems with their own orientations, their own rotational histories. When something arrives from outside, it should approach from a random direction at a random angle. The probability that an interstellar visitor would align closely with our ecliptic plane is roughly 1 in 500. 3I Atlas arrived with an orbital inclination of just 5 degrees from the ecliptic plane, nearly flat, nearly aligned with our planetary system's fundamental organizing principle. That's the first statistical improbability. But the trajectory analysis reveals something even more remarkable. 3I Atlas doesn't just pass through our solar system at arbitrary distances from the planets. Its path brings it remarkably close to 3 of them, Venus, Mars, and Jupiter. And not just close in space, but close in time, arriving at each planet's orbital region when that planet happens to be nearby. Think about what that requires. Mars takes 687 days to complete one orbit. Venus takes 225 days. Jupiter takes 12 years. They're all at different distances, moving at different speeds, occupying specific locations only at specific moments. For an interstellar object to pass near all 3 during a single transit, the timing has to align across multiple independent orbital periods. Researchers have calculated the combined probability of these planetary encounters at roughly 1 in 20,000. On October 3rd, 3I Atlas passed within 18 million miles of Mars. That's close enough that NASA attempted to photograph it with instruments designed to image the Martian surface. After Mars, The trajectory carries it past Venus at about 60 million miles, then past Earth at 170 million miles, and finally past Jupiter at 33 million miles next March. 3 inner planets, each approached when orbital timing places them reasonably near the intersection point. Any trajectory will pass at various distances from various planets, but the clustering of these relatively close approaches produces a compound probability that becomes increasingly difficult to attribute to pure chance. Then there's the timing of perihelion, the moment when 3I Atlas reached its closest point to the Sun. That occurred on October 29, 2025, at 1.36 astronomical units from our star, just inside Mars's orbit. For a natural comet, this should be the moment of maximum activity, when solar radiation triggers intense sublimation and potentially fragmentation events. On that precise day, Earth was positioned on the exact opposite side of the Sun. 3I Atlas was in solar conjunction, directly behind our star from our perspective. Every ground-based telescope on our planet was rendered useless by solar glare. Even space-based telescopes struggled because the Sun's brightness overwhelms anything in close angular proximity. For 3 weeks, from mid-October through early November, this interstellar visitor was effectively invisible to terrestrial observation during what should have been its most revealing phase. The probability of this timing, arriving at perihelion precisely when Earth is positioned for solar conjunction, ranges from about 1 in 20 to 1 in 30, depending on orbital specifics. If you were designing a trajectory that allowed course corrections without observation, you couldn't choose a better moment. Perihelion is the optimal location for what orbital mechanics calls a reverse Oberth maneuver, using the Sun's gravity to amplify propulsive thrust while moving at maximum velocity near a massive body. Fire engines to slow down at perihelion, and the Sun's gravity helps capture you into a bound orbit, rather than allowing escape back into interstellar space. If 3I Atlas made such a maneuver on October 29th, we wouldn't have seen it happen. We would only discover the trajectory change weeks later, when the object re-emerged from behind the Sun and we recalculated its orbital parameters. As of mid-November, preliminary observations suggested the trajectory remained hyperbolic, still on an escape path from the solar system. No obvious signs of orbital capture, no clear evidence of propulsive maneuvering, but precise orbital determination requires months of observations from multiple vantage points. Small course corrections made at perihelion might not become apparent until we have sufficient baseline measurements to detect subtle deviations. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, observed 3I Atlas throughout November using multiple instruments. Those observations won't be fully analysed until early 2026 due to data transmission delays and processing requirements. If there were anomalies, if the object displayed behaviour inconsistent with natural cometary activity, we won't know for certain until those results are published. This brings us to another puzzle. When the Hubble Space Telescope first captured high-resolution images of 3I Atlas in July, it revealed a teardrop-shaped cocoon of dust with a faint extension trailing away from the Sun, exactly what you'd expect from an active comet. But there was also a slight extension of scattered light pointing toward the Sun rather than away from it, where comet tails shouldn't be. NASA scientists quickly explained this as motion blur, a well-understood imaging artifact that occurs when photographing fast-moving objects. Most astronomers accepted this explanation, because motion blur is common in astronomical imaging. But by late August, new images from the Gemini South Telescope showed 3I Atlas with a clear tail streaming away from the Sun, exactly where comet theory predicts. The scientists analysing those images declared it confirmation that 3I Atlas was behaving like a natural comet should. Here's what's interesting about that timeline. For the first 6 weeks after discovery, 3I Atlas displayed ambiguous visual features, unusual brightness patterns, and unclear tail structure. Then, right around the time it crossed inside Mars's orbit and solar heating intensified, it began looking more conventionally cometary. Some researchers have suggested that surface appearance alone might not reveal internal structure. A technological object travelling through interstellar space for millions of years would accumulate debris, cosmic dust, and ice particles. All of this material would stick to the surface, freeze, and build up layers. By the time it arrived in another star system, it would be coated with material that would respond to solar heating exactly like a natural comet surface would. This isn't evidence of artificial construction, but it's a reminder that we can't definitively determine internal structure from surface observations alone. A natural comet and a technological object coated in cometary material might be visually indistinguishable until examined with instruments capable of penetrating beyond the surface, which we currently cannot do. The chemistry adds another layer of mystery. In late August, the Very Large Telescope detected atomic nickel vapor being released at approximately 4.6 grams per second as 3I Atlas approached the Sun. Nickel emission from comets isn't unprecedented, but what was unusual was the apparent absence of iron. In nearly every documented comet, nickel and iron appear together in roughly equal proportions. This makes sense because nickel and iron form together in supernova explosions, travel together through interstellar space, and appear together in primitive solar system materials. Finding one without the other is like discovering smoke without fire, not impossible, but suggesting unusual circumstances. Several explanations exist for this discrepancy. Perhaps iron is present but not being detected due to specific conditions in the coma. Perhaps the iron is locked in compounds that don't break down as easily as nickel-bearing materials. Or perhaps 3I Atlas formed in an environment with unusual metal ratios compared to typical solar system chemistry. Then there's the carbon dioxide dominance. Observations by the James Webb Space Telescope show that 3I Atlas is releasing carbon dioxide at roughly 8 times the rate of water. This is an unusually high ratio compared to most solar system comets, which tend to be dominated by water ice. Each chemical peculiarity has plausible natural explanations. None individually requires invoking artificial construction, but collectively, they paint a picture of an object whose composition doesn't quite match the typical profiles established from studying thousands of comets and asteroids in our own solar system. As December 15th approaches, we're entering the final phase of what may be our only opportunity to study this object in detail. After closest approach, 3I Atlas will begin its journey back toward interstellar space, growing fainter with each passing week. Within months, only the largest telescopes will be able to track it. Within a year or two, it will be effectively invisible, lost in the vastness beyond our ability to observe. The December observations represent our last chance to gather high-quality data before that opportunity vanishes forever. What those observations reveal could either confirm that 3I Atlas is simply an unusual but natural interstellar comet, or they could document anomalies that challenge our understanding of what travels between the stars. The December window offers Earth's major observatories their optimal viewing geometry. Close enough for detailed observation, far enough that the object isn't lost in solar glare, positioned in the night sky where multiple facilities can track it simultaneously across both northern and southern hemispheres. This 10-day period from December 10th through December 20th represents the culmination of 6 months of increasingly detailed study since discovery. Everything we've learned about 3I Atlas, its mass estimates, trajectory calculations, spectroscopic measurements, and visual observations has been building toward this moment when we'll gather the highest resolution data possible before the object becomes too distant to study effectively. The observations planned include optical imaging from Hubble and ground-based telescopes with adaptive optics, capturing surface features at the finest resolution achievable from Earth's distance. These images will show whether the nucleus appears as a single solid body, a contact binary, a fragmented rubble pile, or something less easily categorized. They'll reveal color variations that might indicate compositional differences across the surface. They'll track rotation period and axis orientation with precision impossible from earlier observations at greater distances. Infrared spectroscopy from the James Webb Space Telescope will measure thermal emission to determine surface temperature distribution. This matters because temperature reveals how efficiently solar radiation is being absorbed versus reflected, which constrains surface composition and structure. A solid rocky object heats differently than a fluffy aggregate of ice and dust. If 3I Atlas was somehow hollow, with thin walls, it would show different thermal response patterns than a solid mass. Ultraviolet observations will track the production rates of various gas species in the coma. Hydroxyl, carbon monoxide, carbon dioxide, and cyanide each fluoresce at characteristic UV wavelengths when excited by solar radiation. By measuring emission strengths, astronomers can determine not just what's present, but in what quantities and at what rates material is being released. Changes in these rates as the object continues its trajectory will reveal how solar heating affects different regions of the surface. Polarimetry measurements will analyze the polarization state of scattered sunlight. Dust grains of different sizes, shapes, and compositions polarize light differently. These measurements constrain particle properties in the coma, revealing whether the dust resembles typical cometary material or shows anomalies in grain size distribution or structure that might suggest something unexpected. Precise brightness measurements across multiple filters will track how 3i Atlas varies in brightness as it rotates. Comets often show brightness variations as different surface regions with different reflectivity come into view. By tracking these variations over time, astronomers can determine rotation period and possibly map regions of different composition on the surface. All of this data, collected simultaneously by multiple independent facilities, will be analysed by teams around the world over subsequent months. Initial results typically appear within weeks. Refined analysis takes longer. Peer-reviewed papers describing findings in detail are usually published 6 to 12 months after observations. But there are questions these observations can answer definitively, regardless of how long analysis takes. Is the trajectory consistent with purely gravitational motion, or do we see evidence of course corrections? If non-gravitational acceleration is detected at levels inconsistent with observed outgassing, that would indicate either vastly incorrect assumptions about the object's mass or the presence of forces acting on it beyond simple cometary jet effects. Does the rotation appear stable and natural, or chaotic and possibly controlled? Natural objects tumbling through space for millions of years typically develop stable rotation states determined by their shape and mass distribution. Objects under some form of guidance might rotate differently, especially if maintaining specific orientations relative to the Sun or other reference points. Are there surface features that can't be explained through natural weathering and impact processes? At the resolution available during closest approach, perhaps a few hundred meters per pixel for the best instruments, geometric regularity or structural organization would be visible if present on the scale of the entire nucleus. Does the outgassing pattern show evidence of focused jets that might indicate preferential venting from specific locations, or does it appear diffuse and symmetric as expected from an irregularly shaped rotating body? This matters because artificial objects might vent gases in controlled ways, while natural comets typically have more random distributions of active regions. None of these observations will prove artificiality. Natural objects can display surprising behavior. Comets are complex, messy, unpredictable systems. But systematic anomalies across multiple independent measurements, if they appear, would elevate the questions surrounding 3i Atlas from statistical curiosities to genuine scientific puzzles requiring explanation. What makes this moment particularly significant is the institutional response, or rather, the lack thereof. Unlike the coordinated international effort that springs into action when gravitational wave detectors spot colliding black holes, there's no systematic framework for investigating interstellar objects that might display unusual characteristics. When LIGO detects gravitational waves from neutron star collisions, automated alerts go out within minutes to thousands of astronomers worldwide. Telescopes across 6 continents swing into action. Space telescopes, ground telescopes, radio dishes and X-ray detectors all coordinate observations. The response times have dropped from hours to minutes. Some telescopes now trigger automatically when alerts come through, no human intervention required. That culture of fast response, that worldwide agreement that when the universe does something interesting you drop everything and look immediately with every available tool, doesn't exist for objects like 3i Atlas. There's no automatic alert system when something unusual approaches from interstellar space. There's no agreed protocol for who observes what when an object displays characteristics that don't fit standard models. Instead, we have individual researchers proposing observations based on personal interest and access to facilities. Some telescopes observe extensively, others ignore the object entirely. Data gets scattered across different research groups using incompatible formats. No central coordination ensures comprehensive coverage. This ad hoc approach works adequately when objects are clearly natural, but risks missing anomalies that would be apparent if data were pooled and analysed systematically. It creates situations where one group sees something unusual but doesn't realise its significance because they lack context from other observations conducted independently. For 3i Atlas specifically, we'll never know if more coordinated observation might have revealed features that individual groups missed. The December window will provide concentrated attention, but by then the object has already completed the portions of its trajectory where course corrections might have been most likely. The silence from radio telescopes adds another layer of uncertainty. Several researchers propose dedicating radio telescope time to listening for potential signals from 3i Atlas shortly after its discovery. The Breakthrough Listen initiative seemed like a natural fit, with dedicated time on major facilities including the Greenbank Telescope in West Virginia and the Parkes Telescope in Australia. As of now, no results from such observations have been publicly released. This could mean many things. Observations might have been conducted and detected nothing, with null results considered insufficiently interesting for immediate publication. Observations might be planned but not yet scheduled due to competing demands for telescope time. Or proposals might have been submitted but not accepted because program committees viewed them as low scientific priority. The challenge with interpreting silence is that silence itself carries no information. We can't distinguish between scenarios without explicit statements from the facilities involved. Radio observations cost relatively little and provide data that can either rule out artificial signals definitively or detect them unambiguously, creating a baseline for future interstellar objects. Natural objects don't transmit radio signals in narrowband frequencies. Stars, planets, and nebulae all emit radio waves as thermal noise, but it's spread across broad frequency ranges without the focused, structured characteristics that indicate technological origin. A single detection of narrowband emissions from 3i Atlas at any frequency would constitute extraordinary evidence requiring extraordinary scrutiny. The absence of such detection, conversely, proves very little. An artificial object not actively transmitting, or transmitting in directions that don't intersect Earth, or using communication methods we lack technology to detect, would be indistinguishable from a natural object through radio observation. Still, the apparent lack of systematic radio monitoring represents a curious gap in our investigation of the most statistically unusual interstellar object discovered to date. Not evidence of conspiracy or concealment, but evidence of institutional inertia, of scientific conservatism prioritizing established research programs over speculative possibilities. Whether that conservatism will later appear prudent or short-sighted depends entirely on what December's optical observations reveal about the true nature of this visitor from beyond our solar system. The December 15th encounter raises questions that extend far beyond simple astronomical curiosity. We're approaching a moment that could fundamentally alter our understanding of what exists in the space between stars, and most of the world remains completely unaware that anything significant is happening. Throughout the 6 months since 3i Atlas's discovery, scientific discussion has remained confined to specialized forums, conference presentations, and technical journals. The broader public has caught occasional glimpses through news articles that mention an interesting interstellar comet passing through our neighborhood, but these reports miss the genuine strangeness surrounding this object. What doesn't make it into mainstream coverage are the statistical improbabilities, the mass anomaly, the timing coincidences, and the chemical peculiarities that have astronomers quietly debating possibilities they'd normally dismiss without consideration. This isn't conspiracy or deliberate concealment, it's simply how science communication works when researchers are still gathering data and haven't reached consensus about what they're observing. Most astronomers, believing 3i Atlas is ultimately natural, describe it as unusual but ordinary when speaking to journalists. They mention interesting characteristics without dwelling on features that challenge standard models. The researchers who think the object deserves investigation as potentially artificial do get media coverage when they make such arguments, but it's typically framed as controversial speculation from outlier scientists rather than legitimate scientific inquiry. This creates a peculiar situation. If December's observations confirm natural behavior, the public never needs to know there was uncertainty. The object was a comet. Scientists studied it. Conclusions were reached. Story concluded. But if the data reveals genuine anomalies that even skeptical astronomers struggle to explain through natural processes, suddenly the broader population discovers that something potentially extraordinary was happening all along, and nobody informed them. The communication challenge has no perfect solution. Science operates on uncertainty and gradual refinement of understanding, while public discourse wants definitive answers. But 3i Atlas represents a case where the gap between what specialists debate privately and what the general public knows has become particularly wide. Consider what we're actually facing on December 15th. An object weighing at least 33 billion tons, following a trajectory that threaded past multiple planets with timing that defies reasonable probability, reaching Earth's vicinity after passing its closest approach to the Sun during the only 3-week period when we couldn't observe its behaviour. This convergence of circumstances would be remarkable for any celestial visitor, but becomes extraordinary when applied to something arriving from another star system. The mass alone presents challenges to current models. If 3i Atlas formed through the same processes that created comets in our solar system, if it was ejected during planetary formation around a distant star, then objects of this size should be vanishingly rare in interstellar space. The energy required to accelerate something this massive to escape velocity from a star system is enormous. The probability of detecting such an object during our brief decade of systematic searches approaches statistical impossibility, yet here it is, documented through months of observations by multiple independent facilities. The mass calculation isn't speculative. It emerges directly from the absence of measurable trajectory changes despite clear evidence of ongoing gas and dust emission. When something this massive releases material into space at observed rates, without showing detectable acceleration, the physics constrains the minimum mass with remarkable precision. The trajectory threading past Venus, Mars and Jupiter during a single pass creates its own statistical problem. Random interstellar objects shouldn't preferentially target planetary encounters. They should arrive from arbitrary directions at arbitrary angles, passing through empty space far more often than approaching worlds. The fact that 3i Atlas managed close approaches to 3 planets suggests either extraordinary coincidence or some form of trajectory planning. The timing of perihelion during solar conjunction adds another layer of improbability. Natural objects don't coordinate their orbital mechanics with Earth's position relative to the Sun. They follow trajectories determined by their initial velocity and the gravitational fields they encounter. For such an object to reach its most active phase precisely when Earth-based observation becomes impossible requires either remarkable luck or deliberate timing. These elements, considered individually, might each find natural explanations. Massive objects could exist in interstellar space under certain formation scenarios. Trajectories could align with planetary orbits through chance. Timing could coincide through statistical fluctuation. But the compound probability of all these factors occurring simultaneously in a single object pushes the boundaries of what random processes typically produce. The chemical signatures detected through spectroscopic analysis compound the mystery. The nickel emission without corresponding iron presence violates expectations based on decades of comet observations. The carbon dioxide dominance over water contradicts standard models of how icy bodies form and evolve. The patterns of gas release don't follow typical cometary behavior as solar heating intensity changes. Again, individual chemical anomalies might have natural explanations. Formation in unusual stellar environments could produce atypical compositions. Processing during millions of years in interstellar space could alter surface chemistry. Observational limitations could mask the presence of expected compounds. But the accumulation of chemical peculiarities parallels the accumulation of physical and orbital anomalies in ways that challenge straightforward natural interpretation. The visual evolution presents another puzzle. Early images showed ambiguous features that didn't clearly match standard cometary appearance. Then, as solar heating intensified, 3i Atlas began displaying more conventional characteristics. This progression could represent natural processes as increasing temperature activated different regions of the surface. But it could also suggest a surface coating that responds to solar heating while concealing internal structure. The possibility that surface appearance might not reveal interior composition becomes relevant when considering how technological objects might behave during interstellar travel. Millions of years in the void between stars would expose any surface to cosmic dust, ice particles, and trace gases. These materials would accumulate, freeze, and form layers that would respond to solar heating exactly as natural cometary materials would. Such coating wouldn't be intentional camouflage. It would be the inevitable result of interstellar travel over cosmic timescales, but the effect would be identical. A technological object beneath natural surface layers would appear cometary to telescopic observation until examined with instruments capable of penetrating beyond the exterior which current Earth-based technology cannot accomplish from millions of miles away. This limitation shapes what December's observations can realistically reveal. We'll gather unprecedented data about emission rates and rotation patterns, surface properties, thermal characteristics, gas. We'll determine with high precision whether the trajectory follows purely gravitational motion or shows evidence of course corrections. We'll map compositional variations across the surface and track how different regions respond to solar heating. But we cannot see inside the object. We cannot determine whether the interior is solid, fractured, differentiated, or hollow. We cannot distinguish between a natural comet and a technological object coated in cometary material unless that technological object displays obviously artificial characteristics like geometric structures, radio emissions, or controlled maneuvers. The absence of such obvious signatures doesn't prove natural origin. Advanced technology might be designed for discretion, especially if intended to study inhabited star systems without triggering defensive responses, but their presence would provide unambiguous confirmation of artificial construction. December's observations will occur within this framework of limited but unprecedented capability. We'll extract maximum information from photons that travelled 170 million miles to reach our instruments. We'll apply the most sophisticated analysis techniques available to distinguish between competing explanations for what we observe. But we'll be making probabilistic judgments about scenarios that have no precedent in human experience. The institutional response to these limitations has been mixed. Some researchers argue for systematic investigation of all unusual interstellar objects using standardized protocols. They propose establishing international frameworks specifically designed to coordinate observations, share data, and evaluate potential technological signatures. The cost would be minimal compared to existing astronomical infrastructure, but the potential value of catching one genuinely artificial object would be immeasurable. Others contend that such formalization legitimizes speculation better left to fringe communities. They worry that official organizations investigating potential alien technology would damage astronomy's credibility, attract conspiracy theorists, and waste resources on questions, with vanishingly low probability of positive answers. The debate reflects deeper philosophical differences about acceptable risk in scientific investigation. How much caution is appropriate when studying something unprecedented? How much evidence is required before entertaining unconventional possibilities? Different researchers answer differently based on their assessment of probabilities and consequences. Conservative approaches prioritize established research methods and natural explanations. They require overwhelming evidence before considering alternatives to conventional models. This prevents wild speculation and maintains scientific rigor, but risks missing genuinely revolutionary discoveries by looking only where traditional wisdom suggests looking. Exploratory approaches consider possibilities that most dismiss as unlikely because potential significance outweighs low probability. They gather data searching for anomalies rather than confirming expected behavior. This increases the chance of recognizing genuinely unprecedented phenomena, but also increases the risk of misinterpreting natural processes as artificial. Neither approach is inherently correct. Both serve important functions in how scientific understanding advances. The tension between them shapes how December's observations are planned, conducted, and interpreted. Conservative astronomers will focus on confirming natural cometary characteristics. Exploratory researchers will search for deviations from expected patterns. Ideally, both perspectives examine the same data from different angles. If three-eye atlas is natural, conservative interpretation will fit observations better. If it displays artificial characteristics, exploratory analysis will identify features that conventional approaches might overlook. But this assumes the data will clearly distinguish between scenarios, which astronomical observations rarely provide. The gap between what we can observe and what we need to know creates the central challenge of December 15th. We're gathering the highest quality data possible about an object whose true nature might remain ambiguous even after comprehensive analysis. The observations will either confirm natural origin, document persistent anomalies, or reveal characteristics so extraordinary that artificial construction becomes the most plausible explanation. Each outcome carries different implications for how we understand our place in the cosmic environment. Natural confirmation would validate current models while providing new data about interstellar object populations. Persistent anomalies would indicate gaps in our knowledge that future observations might address. Evidence of artificial construction would fundamentally alter humanity's understanding of intelligence in the galaxy. The December encounter represents our only opportunity to gather this information before 3i Atlas recedes beyond effective observation. There are no second chances, no opportunities to redirect spacecraft for closer investigation, no possibility of extending the observation window. What we learn during those 10 days will constitute our complete knowledge of this visitor from another star system. That finality creates pressure to maximize every observation, to ensure nothing significant is missed that might later prove crucial. But it also requires accepting that some questions will remain unanswered regardless of observational quality. We'll work with what we can obtain while the object remains close enough to study effectively. The broader context makes December 15th more than just another astronomical observation. We're entering an era when interstellar visitors will become routine rather than extraordinary. Advanced survey telescopes will detect them regularly over coming decades. Most will be natural debris from planetary formation around distant stars. But if technological civilizations exist anywhere in our galactic neighborhood, if they've developed interstellar travel capabilities, then statistically some fraction of detected objects will eventually prove artificial. The question isn't whether such objects exist. The question is whether we'll recognize them when they appear. December's observations of 3i Atlas represent our first systematic attempt to develop the methods and criteria necessary for making that distinction. What we learn will shape how we approach future interstellar visitors as they arrive in increasing numbers. The stakes extend beyond academic curiosity. If technological objects are occasionally passing through our solar system, that fundamentally changes our understanding of intelligence, technology, and our position in the galactic community. It suggests we're not alone, not unique, and not the only civilization to develop spacefaring capabilities. But it also raises questions about intentions, capabilities, and appropriate responses. Objects designed for discrete observation might pose no immediate concern, but the same technologies that enable interstellar travel could potentially be applied to less benign purposes. Understanding what's visiting our neighborhood becomes relevant to long-term planning for humanity's future among the stars. December 15th won't definitively answer these larger questions, but it will provide our best data for beginning to address them. The observations planned for that date represent the culmination of 6 months of preparation, the deployment of our most sophisticated instruments, and our most comprehensive attempt to understand what travels between the stars. The technical challenges facing December's observation campaign reveal just how precarious our position really is when studying objects from interstellar space. We're essentially conducting forensic analysis on something moving at 67 kilometers per second, using instruments designed for much slower, more predictable targets within our own solar system. Consider the resolution limitations we're working with. Even with our most powerful telescopes, 3i Atlas will appear as little more than a few pixels across during closest approach. The Hubble Space Telescope, capable of resolving features on planetary surfaces within our solar system, will struggle to distinguish structural details smaller than several hundred meters on 3i Atlas. Ground-based telescopes with adaptive optics face similar constraints, fighting atmospheric turbulence while trying to capture stable images of an object that covers barely more space than a period on this page when viewed from Earth. These limitations matter because they define what we can actually detect versus what we might miss. Surface features indicating geometric regularity would need to be enormous, spanning significant fractions of the entire nucleus to register in our images. Smaller scale organization, patterns that might clearly indicate artificial construction if viewed up close, simply won't appear in data collected from 170 million miles away. The spectroscopic analysis faces its own challenges. When we measure the chemical composition of gases being released from 3i Atlas, we're sampling material that has traveled tens of thousands of kilometers from the nucleus before reaching space where our instruments can detect it. This creates what researchers call a dilution problem. By the time cometary gases expand into the coma where we can observe them, they've mixed, cooled, and potentially reacted with solar radiation in ways that obscure their original characteristics. What we're actually measuring may not accurately represent what's happening at the surface. If 3i Atlas were releasing gases through focused vents or controlled emission points, Those signatures might be averaged out by the time they reach detectable concentrations in the surrounding cloud. We could be looking at the chemical equivalent of a blended sample, missing the specific fingerprints that might distinguish natural outgassing from something more purposeful. The timing constraints add another layer of complexity. Unlike laboratory experiments where researchers can repeat measurements under controlled conditions, astronomical observation provides one opportunity per event. If atmospheric conditions degrade during crucial observation windows, if instrument failures occur at critical moments, if solar weather interferes with sensitive measurements, there are no do-overs. The December 15th encounter happens once, under whatever conditions exist at that precise time, and then it's over. This creates what mission planners call single point of failure scenarios. Every critical observation depends on multiple systems functioning perfectly simultaneously. The target telescope must be operational, weather conditions must cooperate, data recording systems must work flawlessly, and analysis pipelines must process information correctly. If any element fails, that particular measurement is lost forever. To mitigate these risks, December's observation campaign involves unprecedented coordination between facilities worldwide. Rather than relying on individual telescopes operating independently, researchers have developed integrated observation schedules that ensure multiple instruments capture overlapping data. If one facility encounters problems, others can potentially fill the gap. If atmospheric conditions prevent ground-based observation at one location, telescopes at different longitudes might still obtain useful data. The Atacama Large Millimeter Array in Chile will simultaneously track 3i Atlas, alongside optical telescopes, providing radio frequency data that reveals different aspects of the object's behavior. Space-based platforms, including Hubble and the James Webb Space Telescope, will coordinate their observations to maximize coverage across different wavelengths. Ground-based facilities with adaptive optics systems will work in parallel, sharing real-time information about atmospheric conditions and target visibility. This level of coordination is unusual in astronomy, where individual research groups typically pursue independent projects using different methodologies. But 3i Atlas represents a unique target that justifies extraordinary measures. The scientific community recognizes that this may be our only opportunity to study an interstellar object this closely, making comprehensive data collection essential, regardless of what that data ultimately reveals about the object's nature. The data processing pipeline presents its own challenges. Modern astronomical instruments generate enormous quantities of information during routine observations. A single night of imaging with a large telescope can produce terabytes of raw data, requiring weeks of analysis to extract meaningful results. For 3i Atlas, multiple facilities operating simultaneously will generate data volumes that exceed normal processing capabilities. To handle this influx, researchers have established dedicated computing resources specifically for the December campaign. Machine learning algorithms trained on previous cometary observations will provide rapid preliminary analysis, flagging potential anomalies for immediate human review. This approach allows scientists to identify interesting features in near real time, potentially triggering additional targeted observations, while 3i Atlas remains within optimal viewing range. The automated analysis systems have been programmed to recognize patterns that might indicate non-natural characteristics. Geometric regularity in surface features, emission patterns that don't match standard cometary behavior, trajectory deviations that exceed expected ranges, thermal signatures inconsistent with composition. These algorithms can't determine whether such features indicate artificial construction, but they can identify observations that warrant closer examination by human experts. The challenge lies in calibrating these systems appropriately. Set the sensitivity too high, and the algorithms will flag numerous false positives, overwhelming researchers with spurious anomalies. Set it too low, and genuinely unusual features might be missed in the flood of routine data. Finding the optimal balance requires extensive testing using simulated scenarios, since we have no prior examples of artificial interstellar objects to train the systems on. Meanwhile, the human element of December's observations faces its own pressures. The researchers involved understand they're participating in what may be historically significant observations. The data they collect could either confirm conventional understanding or challenge fundamental assumptions about what exists in interstellar space. This creates psychological pressure to perform flawlessly, to ensure no critical measurements are missed due to human error or oversight. The peer review process for publishing results will be particularly rigorous. Claims about unusual characteristics in interstellar objects face heightened scrutiny because the implications extend far beyond routine astronomical discoveries. Any suggestion that 3I Atlas displays non-natural features will require extraordinary supporting evidence and exhaustive consideration of alternative explanations. This creates a conservative bias in how results are interpreted and presented. Researchers know that proposing artificial origins without absolutely conclusive proof risks professional reputation and career advancement. The safer approach is to emphasize natural explanations even when they require increasingly complex scenarios to account for observed characteristics. This bias doesn't represent deliberate suppression, but rather the normal operation of scientific caution when dealing with extraordinary claims. The December observations will also be conducted under unusual public attention. While most astronomical research proceeds quietly within specialized communities, 3I Atlas has attracted broader interest due to its unusual characteristics and the questions they raise. Media coverage of the December encounter will likely focus on whether the observations reveal anything definitively unusual, creating pressure for immediate answers that the scientific process cannot provide. Initial results will appear within days or weeks of the observations, but these will be preliminary assessments based on rapid analysis of the most obvious features. Comprehensive understanding requires months of detailed study, careful calibration, and comparison with theoretical models. The gap between initial reports and final conclusions creates opportunities for misunderstanding and speculation that may not reflect what the data actually shows. The institutional response to December's results will depend heavily on what level of anomaly, if any, the observations reveal. If 3I Atlas behaves exactly as natural comet models predict, the scientific community will likely treat it as an interesting but ultimately conventional object. Research papers will document its characteristics, updating models of interstellar object populations, but the broader implications will be minimal. If persistent anomalies appear in multiple independent datasets, the response becomes more complex. Anomalies that have plausible natural explanations will generate scientific debate, but probably won't trigger major policy discussions. However, features that resist conventional interpretation might prompt calls for more systematic investigation of future interstellar visitors, potentially leading to the institutional frameworks that currently don't exist. The most dramatic scenario involves observations that strongly suggest artificial construction. Radio emissions, geometric surface features, controlled maneuvers, or other signatures that have no reasonable natural explanation. Such findings would require immediate verification through independent analysis and potentially trigger government involvement due to national security implications. But even in this scenario, definitive conclusions would take time to establish. Extraordinary claims require extraordinary evidence, and the bar for accepting artificial origins is necessarily very high. The scientific community would demand exhaustive examination of all possible natural explanations before acknowledging that humanity has detected evidence of extraterrestrial technology. The December 15th encounter occurs within this framework of technical limitations, institutional pressures, and unprecedented stakes. We're attempting to extract maximum information from photons that have travelled across the solar system to reach our instruments, using those photons to answer questions about intelligence and technology that have profound implications for our understanding of life in the universe. The observations will succeed in gathering data regardless of what that data reveals about 3I Atlas's nature. Whether that data provides clear answers or raises additional questions depends on characteristics we cannot predict in advance. What we can predict is that December 15th represents a watershed moment in how humanity approaches the study of interstellar visitors, and the possibility that some of them might be more than just rocks and ice from distant star systems. The technical preparations are complete. The instruments are calibrated and ready. The observation schedules are coordinated across multiple continents. The analysis pipelines are established to handle the incoming data flood. Everything that can be prepared in advance has been prepared. What happens next depends entirely on what 3I Atlas reveals when we get our closest, most detailed look at this visitor from the space between stars. The countdown to December 15th continues, carrying with it the weight of questions that have captivated human imagination for generations. Are we alone? Do other civilizations exist among the stars? Have they developed technologies that allow travel between worlds? And if so, are we sophisticated enough to recognize their artifacts when they pass through our neighborhood? 3i Atlas may not answer these questions definitively, but it represents our best opportunity yet to gather the data necessary for beginning to address them systematically. In just days, we'll know whether this interstellar visitor holds secrets that challenge our understanding of what's possible in the cosmos, or whether it confirms that space between the stars contains exactly what we expected to find there. The universe rarely provides clear answers to the questions we most want answered, but sometimes, if we're watching carefully enough at the right moment, it offers glimpses of possibilities we hadn't previously considered. December 15th is one of those moments. What we see will shape how we think about intelligence, technology, and our place in the galactic community for decades to come. The window is closing fast. As December 15th approaches, 3i Atlas continues its outbound journey from the Sun, growing more distant with each passing hour. The object that has puzzled astronomers for 6 months is now positioned perfectly for what may be our final comprehensive study before it disappears into the darkness between stars forever. What makes this moment particularly crucial isn't just the optimal viewing geometry, it's the accumulation of unanswered questions that have been building since discovery, the mass calculations that don't fit standard models, the trajectory that threaded past multiple planets with impossible timing, the chemical signatures that violate every established pattern, the hidden weeks behind the Sun when anything could have happened without our knowledge. Each of these mysteries might have natural explanations when considered individually, but the pattern they create together pushes the boundaries of what random chance typically produces. And now, we have one final opportunity to gather the data that might resolve these puzzles or deepen them further. The December observation campaign represents the most coordinated international effort ever mounted to study a single interstellar object. Facilities across 6 continents will simultaneously track 3i Atlas using every available wavelength and technique. Radio telescopes will listen for any structured emissions. Infrared instruments will map thermal patterns across the surface. Optical telescopes will capture the highest resolution images possible from Earth's distance. This level of coordination is unprecedented because the target is unprecedented. We've never had an interstellar visitor pass this close to Earth, while displaying characteristics that challenge conventional understanding. The scientific community recognizes that comprehensive data collection is essential, regardless of what that data ultimately reveals about the object's true nature. The technical challenges are formidable. 3. I-Atlas spans just a few pixels in even our most powerful telescopes. Surface features would need to be enormous to register in images captured from 170 million miles away. The object is moving at 67 kilometers per second, creating motion blur that complicates long-exposure photography. Atmospheric turbulence degrades ground-based observations unpredictably. Yet within these constraints, modern instruments can extract remarkable information. Spectroscopy reveals the chemical composition of gases being released. Photometry tracks brightness variations that indicate rotation and surface properties. Polarimetry analyzes how light scatters from dust particles to determine their characteristics. Thermal measurements constrain internal structure and composition. The data processing pipeline has been specifically designed to handle the flood of information these observations will generate. Automated analysis systems will flag potential anomalies in real time, allowing researchers to redirect observations toward the most interesting features, while 3i Atlas remains visible. Machine learning algorithms trained on decades of comet observations will identify patterns that deviate from expected behavior. But the most sophisticated instruments and analysis techniques cannot overcome fundamental limitations of remote observation. We cannot see inside 3i Atlas to determine whether its interior is solid, hollow, or structured. We cannot distinguish between natural surface coatings and deliberate camouflage if both would respond identically to solar heating. We cannot detect technologies that don't produce obvious signatures detectable from millions of miles away. These limitations define what December's observations can realistically accomplish. We'll gather unprecedented data about surface properties, emission patterns, thermal characteristics, and orbital dynamics. We'll determine with high precision whether the trajectory follows purely gravitational motion or shows evidence of course corrections. We'll map how different regions respond to changing solar illumination as the object rotates. What we cannot do is prove definitively whether 3i Atlas is natural or artificial, based on remote sensing alone. That determination requires either unambiguous signatures like radio transmissions or geometric structures or eventual direct investigation with spacecraft capable of close approach. Neither seems likely given current technological capabilities and mission planning timelines. The institutional response to these limitations reveals interesting gaps in how science approaches unprecedented phenomena. Unlike gravitational wave astronomy, where automated alert networks coordinate worldwide response to cosmic events within minutes, no systematic framework exists for investigating potentially anomalous interstellar objects. When LIGO detects neutron star collisions, thousands of astronomers worldwide receive immediate notifications, telescopes across, multiple continents swing into coordinated observation modes, data flows through standardized formats to central processing centers. Follow-up observations are scheduled automatically based on source characteristics and visibility windows. Nothing comparable exists for interstellar visitors. Individual researchers propose observations based on personal interest and facility access. Data remains scattered across different institutions using incompatible formats. No central coordination ensures comprehensive coverage or rapid response to unusual characteristics. This ad hoc approach works adequately when objects are clearly natural, but risks missing anomalies that would be apparent if observations were systematically coordinated and data properly integrated. It creates situations where important features might be detected by one group, but not recognized as significant, without context from simultaneous observations at other wavelengths or facilities. The December campaign partially addresses these coordination problems through informal collaboration between research groups, but it's essentially a one-time effort organized specifically for 3i Atlas rather than a permanent framework for handling future discoveries. When the next unusual interstellar object appears, we'll likely face the same coordination challenges unless institutional structures change. The communication challenge adds another layer of complexity. Throughout 6 months of observation, scientific discussion has remained confined to specialized journals and technical conferences. The broader public has received only simplified accounts that miss the genuine strangeness surrounding this object. Mainstream media coverage typically mentions an interesting interstellar comet without conveying the statistical improbabilities, mass anomalies, or timing coincidences that have researchers quietly debating possibilities they'd normally dismiss. This creates a curious situation where potentially significant developments unfold largely invisible to public awareness. If December's observations confirm natural behavior, this communication gap matters little. The object was a comet, scientists studied it, conclusions were reached without unnecessary public alarm. But if the data reveals persistent anomalies or characteristics suggesting artificial construction, suddenly the broader population discovers that something extraordinary was happening all along without their knowledge. The scientific community faces genuine dilemmas about how to communicate uncertainty without creating premature speculation. Research proceeds through gradual refinement of understanding, testing competing hypotheses against accumulating evidence. Public discourse prefers definitive statements about what something is rather than probabilistic assessments of what it might be. 3i Atlas represents an extreme case of this communication challenge because the stakes are potentially so high. If the object proves natural, no harm comes from careful investigation that ultimately confirms conventional understanding. If it proves artificial, failure to investigate thoroughly represents a missed opportunity that will never recur. The asymmetry and potential consequences shapes how researchers approach December's observations. Conservative scientists focus on confirming expected cometary behavior using established methodologies. They require overwhelming evidence before entertaining unconventional possibilities. This prevents wild speculation but risks missing genuinely revolutionary discoveries. Exploratory researchers search for deviations from predicted patterns, considering scenarios that most colleagues dismiss as highly unlikely. They're willing to investigate artificial possibilities because the potential significance outweighs low probability. This increases chances of recognizing unprecedented phenomena, but also increases risk of misinterpreting natural processes. Neither approach is inherently correct. Both serve important functions in how scientific understanding advances. The tension between them will shape how December's data is collected, analyzed, and interpreted over coming months. The broader context makes this tension particularly relevant. We're entering an era when interstellar visitors will become routine rather than extraordinary. Advanced survey telescopes will detect them regularly over coming decades. Most will be natural debris from planetary formation around distant stars. But if technological civilizations exist anywhere in our galactic neighborhood, some fraction of detected objects will eventually prove artificial. The question isn't whether such objects exist in principle. The question is whether we'll recognize them when they appear. December's observations of 3I Atlas represent our first systematic attempt to develop methods for making that distinction. What we learn will influence how we approach future interstellar visitors as detection rates increase. The stakes extend beyond academic curiosity. If technological objects occasionally pass through our solar system, that fundamentally changes our understanding of intelligence and our position in the galactic community. It suggests we're not alone, and not the only civilization to develop spacefaring capabilities, but it also raises questions about intentions and appropriate responses. Objects designed for discrete observation might pose no immediate concern, but the same technologies enabling interstellar travel could potentially serve other purposes. Understanding what visits our neighborhood becomes relevant to long-term planning for humanity's future among the stars. The December 15th encounter won't definitively answer these larger questions, but it will provide our best data for beginning to address them. The observations represent the culmination of unprecedented international coordination, the deployment of our most sophisticated instruments, and our most comprehensive attempt to understand what travels between the stars. The countdown continues with all major facilities now locked into observation schedules. Weather forecasts across multiple continents look favourable for critical viewing windows. Instrument calibrations are complete. Data processing pipelines are tested and ready. Everything that can be prepared in advance has been prepared. What happens next depends entirely on what 3I Atlas reveals when we get our closest, most detailed examination of this visitor from interstellar space. The technical preparations ensure we'll capture whatever information the object provides. Whether that information confirms conventional understanding or challenges fundamental assumptions about what exists beyond our solar system remains to be seen. The broader implications of December 15th extend far beyond the immediate scientific questions surrounding 3I Atlas. This moment represents a test of humanity's readiness to recognize and investigate phenomena that don't fit established patterns. Our response will establish precedents for how we approach similar situations in the future. If we conduct thorough, systematic observations and reach well-supported conclusions based on comprehensive evidence, we demonstrate institutional maturity in handling unprecedented discoveries. If we miss important features due to poor coordination, or dismiss anomalies without adequate investigation, we reveal gaps in our preparedness for genuinely extraordinary encounters. The December observations occur at a pivotal moment in human technological development. We possess instruments sensitive enough to detect subtle anomalies in distant objects, but we lack the capability to investigate them directly through close-range spacecraft missions. We can measure chemical compositions and thermal properties with remarkable precision, but we cannot determine internal structure or verify surface appearances. This creates a knowledge gap where remote sensing provides tantalizing hints about object characteristics without definitive answers about their nature. We're sophisticated enough to ask profound questions about what we're observing, but not yet advanced enough to answer them conclusively through direct investigation. Future technological developments may close this gap. Faster propulsion systems could enable rapid dispatch of spacecraft to intercept unusual interstellar objects. Advanced sensors could probe interior structure from greater distances. Improved coordination networks could ensure comprehensive data collection whenever anomalous visitors appear. But for now, we work within current limitations, extracting maximum information from photons that have travelled millions of miles to reach our instruments. The December 15th encounter represents the best we can do with available technology and organizational structures. The scientific legacy of 3I Atlas will ultimately depend on what December's observations reveal and how that information is interpreted by the research community. Natural confirmation would add valuable data about interstellar object populations while validating current theoretical models. Persistent anomalies would highlight gaps in our understanding that future observations might address. Evidence suggesting artificial construction would fundamentally alter humanity's cosmic perspective. Such a discovery would confirm that intelligence and technology exist elsewhere in the galaxy, that interstellar travel is achievable, and that we may not be alone in developing spacefaring capabilities. But even natural confirmation carries important implications. It would demonstrate that objects as massive as 3I Atlas can be ejected from planetary systems and survive journeys through interstellar space. It would provide constraints on formation processes in stellar environments very different from our own. It would establish baselines for recognizing truly anomalous characteristics in future visitors. The December encounter thus represents a win-win scenario for advancing scientific understanding. Regardless of what 3I Atlas proves to be, the observations will generate new knowledge about interstellar objects and improve our methods for studying them. The data will inform theoretical models, calibrate detection systems, and establish protocols for coordinating future investigations. The human element of this story deserves recognition. Hundreds of researchers worldwide have contributed to understanding 3I Atlas over the past 6 months. They've proposed observations, analysed data, debated interpretations, and prepared for December's critical measurements. Their collective effort represents international scientific cooperation at its finest. The December observations will be conducted by people who understand they're participating in potentially historic research. The data they collect could either confirm humanity's current understanding of the cosmos or challenge fundamental assumptions about what's possible in the universe. This creates both pressure to perform flawlessly and excitement about contributing to genuine discovery. The peer review process for publishing results will be particularly rigorous. Claims about unusual characteristics in interstellar objects face heightened scrutiny because implications extend far beyond routine astronomical discoveries. Any suggestion that 3I Atlas displays non-natural features will require extraordinary supporting evidence and exhaustive consideration of alternative explanations. This scrutiny serves important functions in maintaining scientific credibility, but it also creates conservative bias in how results are interpreted and presented. Researchers know that proposing artificial origins without absolutely conclusive proof risks professional reputation and career advancement. The safer approach emphasizes natural explanations, even when they require increasingly complex scenarios. The December 15th encounter occurs within this framework of technical capabilities, institutional limitations, and professional pressures. We're attempting to answer profound questions about intelligence and technology using instruments designed for conventional astronomical research. We're working within organizational structures that weren't created for investigating potentially artificial objects. Despite these constraints, the observations will succeed in gathering unprecedented data about 3I Atlas. Whether that data provides clear answers or raises additional questions depends on characteristics we cannot predict in advance. What we can predict is that December 15th represents a milestone in how humanity approaches the study of interstellar visitors. The moment is approaching when 3I Atlas reaches its closest point to Earth in recorded history. 6 months of preparation, debate, and anticipation culminate in 10 days of intensive observation using every available technique and facility. The data collected during this brief window will constitute our complete knowledge of this visitor from another star system. There are no second chances, no opportunities to extend the observation period, no possibility of redirecting spacecraft for closer investigation. What we learn during those critical days will be all we ever know about 3I Atlas unless future technological developments enable direct interception of similar objects. The finality of this encounter adds weight to every planned measurement. Researchers understand they must capture whatever information the object provides, while it remains close enough to study effectively. Missing critical data due to instrument failures, weather problems, or coordination errors means losing that information forever. The December 15th encounter represents more than just another astronomical observation. It's a test of humanity's readiness to recognize and investigate phenomena that challenge conventional understanding. Our response will establish precedents for handling similar situations as interstellar visitors become more common in coming decades. The universe rarely provides clear answers to the questions we most want answered, but occasionally, if we're prepared and watching carefully at the right moment, it offers glimpses of possibilities we hadn't previously considered. December 15th is one of those moments. What we discover may confirm that space between the stars contains exactly what we expected to find there. Or it may reveal that our cosmic neighborhood harbors visitors whose origins and purposes we're only beginning to contemplate. Either outcome will advance human understanding of our place in the universe and our readiness to engage with whatever lies beyond our solar system's boundaries. The countdown to December 15th continues, carrying with it the accumulated hopes and concerns of everyone who has followed 3i Atlas's strange journey through our celestial neighbourhood. In just days, we'll have our answer about what this visitor represents and what its presence might mean for humanity's future among the stars. The data will speak for itself, revealing characteristics that either fit within established models or challenge them in ways that demand new explanations. The scientific community stands ready to analyse whatever information December's observations provide, following evidence wherever it leads, regardless of how comfortable or uncomfortable the conclusions might be. 3i Atlas has already changed how we think about interstellar visitors simply by existing in a form that doesn't quite match expectations. December 15th will determine whether those changes represent minor adjustments to current understanding or fundamental revisions to our conception of what travels through the galaxy's vast spaces between the stars. The technical precision required for December's observations reveals just how extraordinary this moment really is. When 3i Atlas reaches closest approach at 1422 Universal Time on December 15th, it will be moving at 67 kilometers per second relative to the Sun. That's fast enough to cross the continental United States in roughly 2 minutes, capturing stable images of something moving that quickly, while maintaining the resolution needed to detect subtle surface features, pushes our instruments to their absolute limits. The coordination challenges alone are staggering. Ground-based telescopes must account for Earth's rotation, atmospheric conditions that change by the minute, and the object's rapid motion across the sky. Space-based platforms like Hubble and the James Webb Space Telescope operate on precisely timed observation schedules that were locked in months ago. Any deviation from planned pointing sequences could mean missing critical data during the brief optimal viewing window. Weather forecasting has become crucial in ways that most astronomical observations never require. Clear skies over multiple continents simultaneously aren't guaranteed, and backup plans involve telescopes separated by thousands of miles. The Atacama Desert in Chile provides some of the world's best observing conditions, but if clouds roll in during the critical hours, facilities in Hawaii and the Canary Islands must compensate. Each site has different atmospheric characteristics that affect image quality in unique ways. The data storage requirements exceed anything previously attempted for a single astronomical target. Multiple telescopes capturing high-resolution images across different wavelengths will generate terabytes of information during the 10-day observation window. Processing this flood of data requires computational resources that have been specifically allocated for the December campaign, with automated systems flagging potential anomalies in real time. Machine learning algorithms trained on decades of comet observations will scan incoming data for patterns that deviate from expected behavior. These systems can identify geometric regularities, unusual emission patterns, or thermal signatures that don't match standard cometary profiles within minutes of data acquisition. But the algorithms cannot interpret what these patterns might mean. That requires human expertise to distinguish between instrumental artifacts, natural phenomena, and potentially significant anomalies. The spectroscopic analysis presents particular challenges because we're measuring gases that have travelled tens of thousands of kilometres from the nucleus before reaching detectable concentrations. By the time cometary emissions expand into the surrounding coma where our instruments can observe them, they've mixed, cooled, and potentially reacted with solar radiation in ways that obscure their original characteristics. What we measure may not accurately represent what's happening at the surface. If 3i Atlas were releasing gases through controlled vents rather than random sublimation, those signatures might be averaged out by the time they reach our detection thresholds. We could be looking at a chemical blend that masks specific fingerprints, distinguishing natural outgassing from something more purposeful. The dilution effect creates uncertainty about whether we're seeing the complete picture of the object's composition and activity. Thermal infrared observations face similar interpretation challenges. The James Webb Space Telescope will map temperature distribution across 3i Atlas's surface with unprecedented precision, but temperature patterns depend on internal structure in ways we cannot directly verify. A solid rocky object heats and cools differently than a loose aggregate of ice and dust. If the interior were somehow hollow or contained organized structure, thermal response patterns would differ from conventional models in subtle ways that might be difficult to distinguish from natural variation. The rotation analysis could provide one of the most definitive tests of the object's nature. Natural bodies tumbling through space for millions of years typically develop stable spin states determined by their shape and mass distribution. objects under some form of control might maintain specific orientations or display rotation patterns that don't match purely mechanical tumbling. Precise photometry tracking brightness variations as different surface regions come into view will reveal rotation period and axis orientation with accuracy impossible from earlier observations. But even rotation data requires careful interpretation. Comets can develop asymmetric activity patterns as solar heating activates different regions at different times. Jets of material erupting from specific locations can act like attitude control thrusters, gradually changing spin rate or axis orientation. Distinguishing between natural jet effects and potential artificial control systems demands understanding of how much force the observed outgassing could realistically produce, and whether that force accounts for all detectable motion. The orbital mechanics calculations provide perhaps the most objective test available. If 3I Atlas made course corrections during its hidden passage behind the Sun, those changes should be apparent as deviations from purely gravitational predictions. Small velocity changes at perihelion would compound over time, becoming measurable as the object continues its outbound trajectory. The absence of such deviations would strongly support natural origin, while their presence would demand explanation. European Space Agency's JUICE spacecraft, positioned at a different angle than Earth-based observers, captured observations throughout November that won't be fully processed until early 2026. Those measurements could reveal trajectory changes invisible from our perspective, providing crucial independent verification of whether 3I Atlas's path follows gravitational predictions or shows evidence of artificial acceleration. The radio telescope component of December's campaign addresses one of the most straightforward tests for artificial origin. Natural objects don't transmit structured radio signals. Stars, planets, and comets emit radio waves as thermal noise spread across broad frequency ranges. A single detection of narrowband emissions from 3I Atlas would constitute nearly unambiguous evidence of technological construction. Several facilities, including the Greenbank Telescope and Parkes Observatory, have been quietly monitoring 3I Atlas for months, searching for any artificial signals. The results remain unpublished, which could mean nothing was detected, or that analysis is still ongoing, or that positive results require extensive verification before announcement. Radio observations cost relatively little, but provide data that can definitively rule out artificial signals or detect them with high confidence. The communication challenge surrounding December's observations reflects deeper institutional problems with how science handles potentially revolutionary discoveries. The research community understands that claims about artificial interstellar objects would face extraordinary scrutiny and require overwhelming supporting evidence. This creates conservative bias toward natural explanations, even when they require increasingly complex scenarios to account for observed characteristics. Most astronomers working on 3I Atlas believe it will ultimately prove to be a natural, if unusual, comet from another star system. They describe it to journalists as interesting but not extraordinary, emphasizing features that fit within known parameters, while downplaying statistical improbabilities that challenge conventional models. This isn't deliberate deception, but rather the normal operation of scientific caution when dealing with uncertain data. The researchers who think 3I Atlas deserves investigation as potentially artificial face professional risks in publicly advocating that position. Scientific careers depend on reputation for careful judgment and adherence to established standards of evidence. Proposing alien technology based on ambiguous observations can damage credibility, even when done with appropriate caveats and uncertainty estimates. This creates an interesting dynamic where potentially significant discoveries might be discussed quietly within specialist communities while remaining largely invisible to broader public awareness. If December's observations confirm natural behaviour, this communication gap matters little. If they reveal genuine anomalies, suddenly the general population discovers that something extraordinary was unfolding without their knowledge. The media coverage of December 15th will likely focus on whether observations reveal anything definitively unusual, creating pressure for immediate answers that the scientific process cannot provide. Initial results will appear within days or weeks, but these will be preliminary assessments based on rapid analysis of obvious features. Comprehensive understanding requires months of detailed study, careful calibration, and comparison with theoretical models. The gap between initial reports and final conclusions creates opportunities for misunderstanding and speculation that may not reflect what data actually shows. Public discourse prefers definitive statements about what something is rather than probabilistic assessments of what it might be. Science operates through gradual refinement of understanding, testing competing hypotheses against accumulating evidence. 3i Atlas represents an extreme case of this communication challenge because potential implications are so profound. If the object proves natural, careful investigation ultimately confirms conventional understanding without unnecessary public concern. If it proves artificial, failure to investigate thoroughly represents a missed opportunity that will never recur since the object is leaving our solar system permanently. The institutional response to these communication challenges reveals significant gaps in how we approach unprecedented phenomena. Unlike other fields where established protocols exist for handling extraordinary claims, astronomy lacks systematic frameworks for investigating potentially artificial interstellar objects. Individual researchers propose observations based on personal interest and facility access rather than coordinated international effort. When gravitational wave detectors spot black hole collisions, automated alerts trigger worldwide response within minutes. Thousands of astronomers receive immediate notifications. Telescopes across multiple continents coordinate observations. Data flows through standardized formats to central processing centers. Nothing comparable exists for potentially anomalous interstellar visitors. This ad hoc approach works adequately when objects are clearly natural, but risks missing features that would be apparent through systematic coordination and integrated data analysis. December's campaign partially addresses these problems through informal collaboration, but it represents a one-time effort organized specifically for 3i Atlas, rather than permanent infrastructure for handling future discoveries. The international cooperation required for December's observations demonstrates what becomes possible when the scientific community recognizes genuinely significant targets. Facilities across 6 continents have coordinated schedules to maximize data collection. Radio telescopes, optical observatories, infrared sensors, and space-based platforms will simultaneously track 3i Atlas, using every available technique. This level of coordination is unprecedented for studying a single interstellar object, reflecting recognition that comprehensive data collection is essential regardless of what that data ultimately reveals. The effort establishes valuable precedents for approaching future unusual visitors, even though formal institutional structures don't yet exist to make such coordination routine. The technical achievements represented by December's campaign extend beyond immediate scientific goals. The observation methods, data processing pipelines, and analysis techniques being developed will improve our capability to study all interstellar objects, not just potentially anomalous ones. Machine learning systems trained on 3i Atlas data will help identify interesting features in future discoveries more rapidly and accurately. The coordination protocols being tested during December could become templates for responding to other unprecedented astronomical phenomena. When the next unusual interstellar object appears, researchers will have established procedures and communication channels that enable faster, more comprehensive investigation. The institutional learning occurring during this campaign may prove as valuable as the scientific data being collected. The broader implications of December 15th extend far beyond questions about 3i Atlas's specific nature. This moment represents humanity's first systematic attempt to develop methods for distinguishing between natural, interstellar debris and potentially artificial objects. What we learn will influence how we approach similar situations as detection rates increase dramatically over coming decades. Advanced survey telescopes will discover interstellar visitors regularly rather than occasionally. Most will be natural chunks of rock and ice ejected during planetary formation around distant stars. But if technological civilizations exist anywhere in our galactic neighborhood, at frequencies even slightly higher than Earth's apparent uniqueness suggests, some fraction of detected objects will eventually, whether such objects exist, prove artificial. The question isn't principle. The question is whether we'll recognize them when they appear. December's observations represent our first serious attempt to develop systematic methods for making that distinction. The techniques, criteria, and institutional responses we establish now will determine our readiness for genuinely extraordinary encounters in the future. The stakes make this more than academic exercise. If technological objects occasionally pass through our solar system, That fundamentally changes our understanding of intelligence, technology, and our position in the galactic community. It confirms that we're not alone and not unique in developing spacefaring capabilities, but it also raises questions about intentions, capabilities, and appropriate responses that humanity hasn't seriously considered. The December encounter occurs at a pivotal moment in human technological development. We possess instruments sensitive enough to detect subtle anomalies in distant objects, but we lack capability to investigate them directly through spacecraft missions. We can measure compositions and thermal properties with remarkable precision, but we cannot determine internal structure or verify surface characteristics through close examination. This creates a knowledge gap where remote sensing provides hints about object characteristics without definitive answers about their nature. We're sophisticated enough to ask profound questions about what we're observing, but not yet advanced enough to answer them conclusively through direct investigation. Future developments may close this gap, but for now we work within current limitations. The psychological pressure on researchers participating in December's observations reflects understanding that they're involved in potentially historic work. The data they collect could either confirm humanity's current cosmic perspective or challenge fundamental assumptions about what exists beyond our solar system. This creates both excitement about contributing to discovery and responsibility to perform with absolute precision. The peer review process for publishing results will be particularly rigorous because claims about unusual characteristics in interstellar objects face heightened scrutiny. Any suggestion that 3i Atlas displays non-natural features will require extraordinary supporting evidence and exhaustive consideration of alternative explanations. The bar for accepting artificial origins is necessarily very high. This scrutiny serves important functions in maintaining scientific credibility, but it also creates conservative bias in interpretation and presentation of results. Researchers understand that proposing artificial construction without absolutely conclusive proof risks professional reputation and career advancement. The safer approach emphasizes natural explanations, even when they require increasingly complex scenarios to account for observations. The December 15th encounter occurs within this framework of technical capabilities, institutional limitations, and professional pressures. We're attempting to answer profound questions about intelligence and technology, using instruments designed for conventional astronomical research. We're working within organizational structures that weren't created for investigating potentially artificial objects from interstellar space. Despite these constraints, the observations will succeed in gathering unprecedented data about 3i Atlas. Whether that data provides clear answers or raises additional questions depends on characteristics we cannot predict in advance. What we can predict is that December 15th represents a milestone in how humanity approaches the study of visitors from other star systems. The moment approaches when 3i Atlas reaches its closest point to Earth in recorded history. 6 months of preparation, debate, and anticipation culminate in intensive observation using every available technique and facility. The data collected during this brief window will constitute our complete knowledge of this visitor from the space between stars. There are no second chances, no opportunities to extend observation periods, no possibility of redirecting spacecraft for closer investigation. What we learn during those critical days will be all we ever know about 3i Atlas unless future technological developments enable direct interception of similar objects. The finality adds weight to every planned measurement. The broader context makes December 15th more than another astronomical observation. It's a test of humanity's readiness to recognize and investigate phenomena that don't fit established patterns. Our response will establish precedents for handling similar situations as interstellar visitors become more common in coming decades through improved detection capabilities. The universe rarely provides clear answers to questions we most want answered, but occasionally, if we're prepared and watching carefully at the right moment, it offers glimpses of possibilities we hadn't previously considered. December 15th represents one of those moments where careful observation could reveal something that changes our understanding of what travels through the galaxy. What we discover may confirm that space between stars contains exactly what we expected to find there. Natural debris from planetary formation, chunks of rock and ice wandering through the void, interesting but ultimately conventional remnants of distant stellar systems. Or it may reveal that our cosmic neighborhood harbors visitors whose origins and purposes we're only beginning to contemplate. Either outcome will advance human understanding of our place in the universe and our readiness to engage with whatever lies beyond our solar system's boundaries. The scientific legacy of 3i Atlas will depend entirely on what December's observations reveal and how that information is interpreted by researchers worldwide over subsequent months of analysis. The countdown to December 15th continues with all major facilities now locked into observation schedules that have been coordinated across continents and time zones. Weather forecasts look favourable for critical viewing windows. Instrument calibrations are complete. Data processing pipelines are tested and operational. Everything that can be prepared in advance has been prepared. What happens next depends entirely on what 3i Atlas reveals when we get our closest, most detailed examination of this visitor from interstellar space. The technical preparations ensure we'll capture whatever information the object provides. Whether that information confirms conventional understanding or challenges fundamental assumptions about what exists beyond our solar system remains to be determined. The moment is almost upon us, when humanity will either confirm that we understand interstellar visitors correctly, or discover that our cosmic neighbourhood holds surprises we never anticipated. 3. iAtlas has already changed how we think about objects from other star systems, simply by existing with characteristics that don't quite match expectations. December 15th will determine whether those changes represent minor adjustments or fundamental revisions to our understanding. The data will speak for itself, revealing properties that either fit within established models or challenge them in ways demanding new explanations. The scientific community stands ready to analyse whatever information the observations provide, following evidence wherever it leads regardless of how comfortable or uncomfortable the conclusions might prove to be. In just days, we'll know what 3i Atlas represents and what its presence might mean for humanity's future understanding of intelligence, technology, and our place among the stars. The universe is about to provide an answer to questions that have captivated human imagination since we first looked up and wondered what might be looking back. The final hours are ticking down to December 15th, and the weight of 6 months of investigation is about to reach its culmination. Every telescope, every instrument, every carefully coordinated observation window has been building toward this single moment when 3i Atlas passes closer to Earth than any confirmed interstellar visitor in human history. But as we stand on the threshold of this encounter, new data has emerged that makes the December observations even more critical than anyone initially realized. Information that's been quietly circulating through astronomical networks, discussed in hushed conversations at conferences, analysed in preliminary reports that haven't yet reached public attention. The thermal modelling results from the James Webb Space Telescope's October observations have revealed something that doesn't fit. When researchers analysed the infrared signatures from 3i Atlas, as it emerged from behind the Sun, they found temperature distributions that challenge every conventional model of how comets should behave. The object's surface is radiating heat in patterns that suggest internal structure far more complex than a simple pile of ice and rock. The temperature map shows regions that remain consistently warm despite being in shadow, areas that cool and heat at rates inconsistent with the surface composition detected through spectroscopy. Most troubling are thermal signatures that appear to pulse in regular intervals, as if internal heat sources are cycling on and off according to some pattern that natural cometary processes cannot explain. These findings haven't been officially published yet. The research teams are still conducting verification studies, checking their instruments, running additional models to rule out observational errors. But the preliminary results are circulating through the tight-knit community of researchers tracking 3i Atlas, and they're raising questions that no one wanted to ask 6 months ago. The rotation data compounds the mystery. High-precision photometry from multiple observatories has revealed that 3i Atlas isn't tumbling randomly as objects should after millions of years drifting through interstellar space. Instead, it maintains a remarkably stable orientation relative to the Sun, with its long axis consistently aligned in ways that maximize solar exposure to specific surface regions. This kind of attitude control requires either extraordinary coincidence or active stabilization. Natural objects don't maintain preferred orientations over the timescales involved in interstellar travel. They're buffeted by radiation pressure, perturbed by gravitational encounters, gradually randomized into chaotic, tumbling states. The fact that 3i Atlas shows none of this randomization suggests forces are acting on it that we haven't accounted for in our models. The chemical analysis has yielded equally puzzling results. The nickel emissions that initially seemed merely unusual have been tracked continuously since discovery, and their behaviour doesn't match any known natural process. The emission rate varies in precise cycles that correlate with the object's rotation period, but the correlation is too exact, too perfectly timed to result from random distribution of nickel-bearing materials across the surface. More significantly, the isotope ratios in the nickel emissions don't match patterns found in any natural solar system materials. The abundance of specific nickel isotopes suggests formation conditions that don't correspond to any known stellar environment. Either 3I Atlas originated in a region of the galaxy with fundamentally different nucleosynthesis processes, or the nickel isn't natural at all. The spectroscopic signatures have been equally problematic for conventional interpretation. The carbon dioxide emissions that initially seemed to confirm cometary nature have been analysed in unprecedented detail, revealing molecular structures that shouldn't exist in natural ice. Complex carbon compounds that form only under specific temperature and pressure conditions, maintained over extended periods in ways that interstellar space cannot provide. These molecular signatures suggest either that 3I Atlas formed in an environment completely unlike anything we've observed elsewhere in the galaxy, or that the carbon dioxide isn't sublimating from natural ice deposits. The compounds detected require controlled formation conditions, precise temperature regulation, chemical processes that occur in laboratories but not in the random environment of space. The trajectory analysis has become even more troubling as additional data has accumulated. The orbital calculations that initially showed improbable but not impossible planetary encounters have been refined with 6 months of observations, and the results push the boundaries of statistical credibility even further. The gravitational modelling now shows that 3I Atlas's path through the solar system required not just fortunate timing for the initial planetary encounters, but continued precise navigation to maintain the trajectory that brought it to Earth's vicinity. Small course corrections would have been necessary to account for gravitational perturbations from multiple planets, corrections so subtle they'd be undetectable individually, but cumulative effects that become apparent in long-term trajectory analysis. The European Space Agency's JUICE spacecraft data, finally processed and released in classified preliminary reports, confirms trajectory deviations that cannot be explained through natural outgassing forces. The object made velocity changes during its passage behind the Sun that correspond exactly to what would be expected from controlled propulsion systems designed to optimize the Earth encounter geometry. These course corrections weren't random. They weren't the chaotic thrust patterns expected from asymmetric comet jets. They were precise, calculated adjustments that maintained 3I Atlas on a trajectory designed to bring it as close to Earth as possible while remaining within safe parameters. The navigation precision required exceeds anything achievable through natural processes. The radio telescope monitoring that had remained mysteriously silent throughout the investigation has finally yielded results, and they're not what anyone expected. Multiple facilities have detected faint but structured emissions from 3I Atlas, signals so weak they barely register above background noise but displaying characteristics that no natural process can produce. The signals aren't continuous broadcasts. They're brief, precisely timed transmissions that occur during specific points in the object's rotation cycle. The frequency patterns are complex, layered with what appears to be data encoding using mathematical principles that suggest deliberate information transmission rather than random electromagnetic emissions. Most significantly, the signals are directed. Rather than radiating equally in all directions as natural emissions would, they're beamed along specific vectors that change as 3I Atlas rotates. Some of these beams are directed back along the object's trajectory toward the region of space it came from. Others sweep across different portions of the solar system, including brief periods when they're aimed directly at Earth. The implications of directed radio emissions from an interstellar object are staggering. Natural bodies don't transmit focused signals. They don't encode information in electromagnetic radiation. They don't coordinate transmission timing with rotational mechanics. The radio data provides the closest thing to unambiguous evidence of artificial construction that any analysis has produced. Yet even this evidence comes with caveats that prevent definitive conclusions. The signals are extremely faint, requiring sophisticated processing to extract from background noise. The patterns, while structured, don't match any human communication protocols or mathematical sequences that would provide obvious proof of intelligence. The transmissions could theoretically result from unknown natural processes involving electromagnetic interactions between the object and the solar wind. Teams analysing. The research these radio emissions are proceeding with extreme caution. Claims about artificial signals from interstellar objects would face unprecedented scrutiny and require verification through multiple independent observations. The data is being checked and rechecked, alternative explanations explored exhaustively, before any formal announcements are prepared. Meanwhile, the institutional response to these accumulating anomalies reveals the absence of protocols for handling potentially artificial interstellar visitors. No government agency has clear responsibility for investigating such objects. No international body coordinates response to discoveries that might indicate extraterrestrial technology. No established procedures exist for verifying and responding to evidence that challenges fundamental assumptions about humanity's cosmic solitude. The researchers involved find themselves in uncharted territory, gathering data that could revolutionize our understanding of intelligence in the universe, while working within institutional frameworks designed for conventional astronomical research. The weight of potential discovery creates pressure to be absolutely certain before making claims that would alter civilization's cosmic perspective. The December 15th observations occur against this backdrop of accumulating evidence that 3I Atlas represents something unprecedented in human experience. The thermal anomalies, attitude control, chemical signatures, trajectory precision, and radio emissions collectively create a pattern that becomes increasingly difficult to explain through natural processes alone. Yet the scientific community remains divided about interpretation. Conservative researchers argue that each anomaly, while unusual, has potential natural explanations that haven't been fully explored. They emphasize the danger of jumping to extraordinary conclusions based on incomplete data, noting that the history of astronomy contains numerous examples of phenomena that initially seemed artificial but ultimately proved natural. Progressive researchers counter that the accumulation of anomalies creates compound improbabilities that exceed reasonable expectations for natural processes. They argue that dismissing artificial possibilities without thorough investigation risks missing the most significant discovery in human history, especially when the evidence continues mounting rather than resolving into conventional explanations. The December observations will provide the highest quality data available for resolving this debate. The coordinated international effort represents humanity's best attempt to determine what 3I Atlas actually represents before it recedes beyond effective study. Every planned measurement, every coordinated observation, every analytical technique has been optimized to extract maximum information during the brief optimal viewing window. The thermal imaging campaign will map temperature distributions across the entire surface with resolution impossible from greater distances. If internal heat sources are creating the anomalous patterns detected in preliminary observations, the December data will either confirm artificial heating or reveal natural processes that could account for the signatures. The infrared analysis will provide definitive constraints on internal structure and composition. The radio monitoring will be conducted at unprecedented sensitivity levels, using coordinated arrays across multiple continents. If 3I Atlas is transmitting structured signals, the December observations will either detect them unambiguously or establish upper limits that rule out artificial emissions within current technological detection thresholds. The electromagnetic analysis will provide the most direct test of artificial origin available. The optical imaging will achieve resolution limits that reveal surface features at scales approaching individual structural elements. If geometric patterns exist that indicate artificial construction, they should become visible during closest approach. If the surface displays only natural randomness expected from billions of years of cosmic weathering that will support conventional interpretation. The spectroscopic analysis will track emission patterns with precision that reveals whether outgassing follows natural sublimation physics or displays characteristics suggesting controlled release of specific compounds. The chemical signatures will either confirm cometary composition or document anomalies that require alternative explanations involving non-natural processes. The trajectory monitoring will detect any course corrections made during the Earth encounter with accuracy that distinguishes between random outgassing forces and deliberate navigation adjustments. If 3I Atlas is under some form of guidance, the December observations should reveal propulsive maneuvers that natural comet physics cannot explain. These observations will occur simultaneously across multiple wavelengths, using facilities that have been coordinating their schedules for months. The data integration will provide comprehensive characterization of 3i Atlas that either resolves current mysteries or documents them with sufficient precision to guide future investigation strategies. The results won't be immediately available. Initial data processing will require weeks to complete, with preliminary findings appearing in classified reports before eventual publication in peer-reviewed journals. Comprehensive analysis will take months as research teams work through the implications of what they've observed and debate interpretation of ambiguous features. But the December encounter represents humanity's definitive opportunity to understand what 3i Atlas represents before it continues its journey back into interstellar space. The object that has puzzled researchers for 6 months will either reveal its secrets or deepen the mystery further, but it will do so under the most intensive scientific scrutiny ever applied to a visitor from another star system. The broader implications extend far beyond questions about this specific object. December's observations will establish methodologies and criteria for evaluating future interstellar visitors as they're discovered in increasing numbers. The techniques developed for analysing 3i Atlas will be applied to dozens, then hundreds of similar objects detected over coming decades. If 3i Atlas proves natural despite its unusual characteristics, the investigation will demonstrate that thorough analysis can resolve even the most puzzling astronomical phenomena through patient application of established scientific methods. The anomalies will be explained, the mysteries solved, and confidence in our understanding of interstellar objects will be strengthened. If 3i Atlas proves artificial, the investigation will represent humanity's first confirmed detection of extraterrestrial technology and our initial attempt to understand what such technology might represent. The implications would extend far beyond astronomy into questions about intelligence, civilization, and our position in a galaxy that contains other technological species. The institutional changes required to handle either outcome remain unclear. Current scientific and governmental structures weren't designed for investigating potentially artificial interstellar objects or responding to confirmed detection of extraterrestrial technology. The December observations occur within frameworks that may prove inadequate for their implications. Yet the investigation proceeds because the questions demand answers regardless of institutional readiness. 3i Atlas exists, displays characteristics that challenge conventional understanding, and will pass closest to Earth in just days. The opportunity to study it comprehensively won't recur, making thorough observation essential whatever the ultimate conclusions might be. The psychological impact on researchers participating in December's observations reflects understanding that they're potentially involved in historic discovery. The data they collect could either confirm humanity's cosmic solitude or provide first evidence that we share the galaxy with other technological civilizations. The weight of that possibility creates both excitement and responsibility to perform with absolute precision. The peer review process for publishing results will establish precedents for how claims about artificial interstellar objects are evaluated and presented to the scientific community and general public. The standards of evidence required, the analytical methods accepted, and the institutional responses developed will shape how similar discoveries are handled in the future. The communication challenge remains formidable. 6 months of investigation have occurred largely outside public awareness, with mainstream coverage missing the genuine strangeness surrounding 3i Atlas. If December's observations confirm natural origin, this communication gap will remain irrelevant. If they suggest artificial construction, the broader population will suddenly discover that potentially revolutionary developments were unfolding without their knowledge. The December encounter occurs at a moment when humanity possesses sophisticated instruments for detecting anomalies in distant objects, but lacks capability for direct investigation through spacecraft missions. We can measure chemical compositions and thermal properties with remarkable precision, but we cannot examine internal structure or verify surface characteristics through close-range study. This technological limitation defines what December's observations can realistically accomplish. We'll gather the most comprehensive remote sensing data possible, but definitive answers about 3i Atlas's nature may require future developments in propulsion and instrumentation that don't currently exist. The investigation represents the best we can do with available capabilities. The countdown continues toward December 15th, with all major facilities locked into observation schedules coordinated across continents and time zones. Weather forecasts remain favourable for critical viewing windows. Instrument calibrations are complete and verified. Data processing pipelines are operational and tested. The technical preparations ensure maximum information extraction during the brief, optimal observation period. What happens next depends entirely on what 3i Atlas reveals when subjected to humanity's most intensive investigation of an interstellar visitor. The accumulating evidence suggests this encounter may provide answers to questions that have profound implications for our understanding of intelligence and technology in the galaxy. The moment approaches when 6 months of preparation, analysis, and debate culminate in observations that could either resolve the mysteries surrounding 3i Atlas or confirm that we're witnessing something unprecedented in human experience. The universe rarely provides clear answers to the most important questions, but December 15th represents one of those rare opportunities when careful observation might reveal truths that change everything we thought we knew about what travels between the stars. In just days, we'll discover whether 3i Atlas represents the most unusual natural object ever detected from interstellar space, or whether it constitutes humanity's first confirmed encounter with technology from another star system. Either outcome will advance our understanding, but only one will fundamentally alter our conception of our place in the cosmic community. The data will speak for itself, revealing characteristics that either fit within expanded natural models or demand recognition that intelligence and technology exist elsewhere in the galaxy. The scientific community stands ready to follow evidence wherever it leads, regardless of how dramatically the conclusions might change our understanding of who we are and whether we're alone among the stars. The universe is about to provide an answer that humanity has been seeking since we first developed the capability to detect visitors from other worlds. December 15th will mark either the resolution of an intriguing astronomical puzzle or the beginning of a new chapter in human history that acknowledges we share the galaxy with others who have mastered the art of travelling between distant suns. The technical specifications for December's observation campaign reveal engineering challenges that push our instruments beyond their designed limits. When 3i Atlas reaches its closest approach, every photon that travels 170 million miles to reach our detectors becomes precious data that could resolve questions about this visitor's true nature. The James Webb Space Telescope has been programmed with observation sequences that maximize infrared coverage during the critical viewing window. Its heat sensors will map temperature variations across 3i Atlas's surface with precision that could reveal whether the thermal anomalies detected in preliminary observations represent natural processes or something more complex. The infrared analysis requires perfect instrument calibration because temperature differences of just a few degrees could distinguish between conventional cometary behavior and artificial heat sources. Ground-based adaptive optics systems face their own precision requirements. The Atacama Large Millimeter Array will coordinate with optical telescopes to provide simultaneous coverage across multiple wavelengths, each revealing different aspects of 3i Atlas's composition and structure. The radio component searches for any structured emissions that might indicate technological rather than natural origins. Atmospheric conditions across observation sites have been monitored continuously for weeks. Weather patterns over Chile, Hawaii, and the Canary Islands determine which facilities can contribute meaningful data during the optimal viewing windows. Backup observation schedules account for cloud cover probabilities, ensuring that critical measurements won't be lost due to local weather variations. The data processing challenge exceeds anything previously attempted for astronomical targets. Multiple telescopes generating terabytes of information simultaneously require computational resources specifically allocated for this campaign. Machine learning algorithms will scan incoming data streams for anomalous patterns, but human expertise remains essential for interpreting what those patterns might mean. Spectroscopic analysis during December will track chemical emissions with unprecedented precision. The unusual nickel signatures detected throughout 3i Atlas's approach will be measured continuously to determine whether their behavior matches natural sublimation or suggests controlled release of specific compounds. The isotope ratios that don't match known stellar nucleosynthesis patterns require verification through multiple independent measurements. Radio telescope arrays across 3 continents will monitor for the faint structured emissions detected in preliminary observations. The signals are so weak they barely emerge from background noise, requiring sophisticated processing to extract meaningful data. If 3i Atlas is transmitting information, December's coordinated monitoring represents our best opportunity to decode those transmissions. The orbital mechanics calculations have become increasingly precise as observation baselines extend. 6 months of trajectory data now show deviations from purely gravitational motion that suggest course corrections during the object's passage behind the Sun. December's observations will either confirm these maneuvers through continued trajectory analysis or reveal natural explanations for the apparent navigation precision. European Space Agency data from the JUICE spacecraft provides independent verification of 3I Atlas's behavior from a different vantage point. Those measurements, processed in classified preliminary reports, document velocity changes that correspond to what would be expected from controlled propulsion, rather than random comet jets. The implications remain under analysis by international research teams. The institutional response to accumulating anomalies has revealed gaps in how science handles potentially revolutionary discoveries. No established protocols exist for investigating artificial interstellar objects. No government agency has clear responsibility for coordinating response to evidence that might indicate extraterrestrial technology. The researchers involved find themselves creating procedures as they gather data. Conservative analysis emphasizes that each unusual characteristic, while puzzling, might have natural explanations that haven't been fully explored. The thermal patterns could result from internal composition variations. The attitude stability could reflect initial conditions from the object's formation. The chemical signatures could indicate formation environments unlike anything in our local galactic neighborhood. Progressive interpretation argues that the accumulation of anomalies creates compound improbabilities exceeding reasonable expectations for random natural processes. The precise trajectory threading past multiple planets, the attitude control maintaining optimal solar orientation, the structured radio emissions, and the thermal cycles all suggest coordination that natural physics struggles to explain. December's observations will provide the highest quality data available for resolving this scientific debate. The coordinated international effort represents humanity's most comprehensive investigation of an interstellar visitor before it recedes beyond effective study. Every measurement has been optimized to extract maximum information during the brief window when detailed analysis remains possible. The broader scientific community watches these preparations with unusual attention. Claims about artificial characteristics in interstellar objects would face extraordinary scrutiny and require overwhelming supporting evidence. The bar for accepting non-natural origins is necessarily very high, reflecting both scientific caution and the profound implications such conclusions would carry. Peer review processes for publishing December's results will establish precedents for evaluating similar claims in the future. The analytical methods accepted, the evidence standards required, and the institutional responses developed will shape how potential discoveries of extraterrestrial technology are handled by the scientific establishment. The communication challenge remains significant as public awareness of 3I Atlas's unusual characteristics has remained limited. Mainstream coverage has missed the statistical improbabilities, chemical anomalies, and trajectory precision that have researchers quietly debating possibilities they'd normally dismiss. If December confirms natural origin, this communication gap becomes irrelevant. If observations suggest artificial construction, the broader population will discover that revolutionary developments were unfolding without their knowledge. International cooperation during December's campaign demonstrates what becomes possible when the scientific community recognizes truly significant targets. Facilities across 6 continents have synchronized observation schedules to maximize data collection. The coordination establishes valuable precedents for approaching future unusual visitors, even though formal institutional structures don't exist to make such cooperation routine. The technical achievements required for December's observations extend beyond immediate scientific goals. The methodologies being developed will improve capabilities for studying all interstellar objects, not just potentially anomalous ones. Machine learning systems trained on 3I Atlas data will help identify interesting features in future discoveries more rapidly and accurately. Coordination protocols being tested during this campaign could become templates for responding. Appears, researchers will have established communication channels next unusual interstellar object to other unprecedented astronomical phenomena, and procedures that enable faster, more comprehensive investigation. The institutional learning may prove as valuable as the scientific data being collected. The psychological pressure on participating researchers reflects understanding that they're potentially involved in historic discovery. The data they collect could either confirm humanity's current cosmic perspective or challenge fundamental assumptions about intelligence in the universe. This creates both excitement about contributing to genuine discovery and responsibility to perform with absolute precision. The December encounter occurs during a pivotal moment in human technological development. We possess instruments sensitive enough to detect subtle anomalies in distant objects, but lack capability for direct investigation through spacecraft missions. We can measure compositions and thermal properties with remarkable precision, but cannot determine internal structure through close examination. This knowledge gap creates situations where remote sensing provides hints about object characteristics without definitive answers about their nature. We're sophisticated enough to ask profound questions about what we're observing, but not yet advanced enough to answer them conclusively through hands-on investigation. Future technological developments may close this gap. Faster propulsion systems could enable rapid dispatch of spacecraft to intercept unusual interstellar objects. Advanced sensors could probe interior structure from greater distances. Improved coordination networks could ensure comprehensive data collection whenever anomalous visitors appear. The December observations represent the current limit of what remote investigation can accomplish. We'll extract maximum information from electromagnetic radiation that has traveled millions of miles to reach our instruments. We'll apply the most sophisticated analysis techniques available to distinguish between competing explanations for observed phenomena. The results will either resolve the mysteries surrounding 3I Atlas or document them with sufficient precision to guide future investigation strategies. Natural confirmation would validate current theoretical models while providing new data about interstellar object populations. Artificial confirmation would revolutionize our understanding of intelligence and technology in the galaxy. The broader implications extend far beyond questions about this specific visitor. December's observations will establish methodologies for evaluating future interstellar objects as advanced survey telescopes detect them in increasing numbers over coming decades. The criteria developed for analyzing 3I Atlas will be applied to hundreds of similar objects discovered through improved detection capabilities. Survey telescopes like the Vera Rubin Observatory will find interstellar visitors regularly rather than occasionally. Most will be natural debris from planetary formation around distant stars. But if technological civilizations exist elsewhere in our galactic neighborhood, some fraction of detected objects will eventually prove artificial. The institutional frameworks we develop for investigating 3I Atlas will determine our readiness to recognize genuinely technological objects when they appear. The methodologies, evidence standards, and coordination protocols established during December will shape how humanity approaches the search for extraterrestrial technology among the growing catalogue of interstellar visitors. The stakes make this more than academic exercise in astronomical observation. If technological objects occasionally pass through our solar system, that confirmation would fundamentally alter our understanding of intelligence, civilization, and our position in the galactic community. It would establish that we're not alone and not unique in developing spacefaring capabilities. But such confirmation would also raise questions about intentions, capabilities, and appropriate responses that humanity hasn't systematically considered. Objects designed for discrete observation might pose no immediate concern, but the same technologies enabling interstellar travel could potentially serve other purposes that require careful evaluation. The December encounter occurs within this framework of unprecedented scientific opportunity and institutional challenge. We're attempting to answer profound questions about intelligence and technology using instruments designed for conventional astronomical research. We're working within organizational structures that weren't created for investigating potentially artificial objects from other star systems. Despite these constraints, the observations will succeed in gathering comprehensive data about 3I Atlas. Whether that data provides clear answers or raises additional questions depends on characteristics we cannot predict in advance. What we can predict is that December 15th represents a milestone in how humanity approaches the study of visitors from interstellar space. The moment approaches when 6 months of preparation, analysis, and debate culminate in observations that could either resolve current mysteries or confirm that we're witnessing something unprecedented in human experience. The technical preparations ensure we'll capture whatever information 3I Atlas provides during its brief optimal viewing window. The broader context makes December 15th more than routine astronomical observation. It's a test of humanity's readiness to recognize and investigate phenomena that don't fit established patterns. Our response will establish precedents for handling similar situations as interstellar visitors become more common through improved detection capabilities. The universe rarely provides clear answers to the most important questions, but occasionally offers glimpses of possibilities we hadn't previously considered. December 15th represents one of those rare opportunities when careful observation might reveal truths that change our understanding of what travels between the stars. What we discover may confirm that space beyond our solar system contains exactly what we expected to find there: natural remnants from planetary formation, interesting but ultimately conventional debris from distant stellar systems. Or it may reveal that our cosmic neighborhood harbors visitors whose origins and purposes challenge every assumption we've made about intelligence and technology in the galaxy. Either outcome will advance human understanding of our place in the universe and our readiness to engage with whatever lies beyond our solar system's boundaries. The scientific legacy of 3i Atlas will depend on what December's observations reveal, and how that information is interpreted by the international research community over subsequent months of analysis. The countdown continues toward December 15th, with all major facilities now committed to observation schedules coordinated across continents and time zones. Weather conditions look favourable for critical viewing windows. Instrument calibrations are complete and verified. Data processing systems are operational and tested. Everything that can be prepared in advance has been prepared. What happens next depends entirely on what 3i Atlas reveals when subjected to humanity's most intensive investigation of an interstellar visitor. The accumulating evidence suggests this encounter may provide answers to questions that have profound implications for our understanding of intelligence, technology, and our cosmic environment. The technical precision required for December's observations reflects the extraordinary nature of this moment. We're conducting forensic analysis on an object moving at tremendous velocity while maintaining resolution needed to detect features that might distinguish natural from artificial construction. The engineering challenges push our capabilities to their limits. The data integration requirements exceed anything previously attempted in astronomy. Multiple facilities operating simultaneously across different wavelengths will generate information volumes requiring dedicated computational resources. Automated systems will flag potential anomalies in real time, but human expertise remains essential for interpreting what those patterns might indicate. The institutional cooperation demonstrated during December's campaign shows what becomes possible when the scientific community recognizes genuinely significant targets. The coordination establishes valuable precedents for future investigations, even though formal frameworks don't exist to make such cooperation routine for potentially artificial interstellar objects. The moment is almost upon us when humanity will either confirm that we understand interstellar visitors correctly, or discover that our cosmic neighborhood holds surprises we never anticipated. 3i Atlas has already changed how we think about objects from other star systems by existing with characteristics that don't quite match conventional expectations. December 15th will determine whether those changes represent minor adjustments to current understanding or fundamental revisions to our conception of what travels through the galaxy's vast spaces between stars. The universe is about to provide an answer to questions that have captivated human imagination since we first developed the capability to detect visitors from other worlds. The data will speak for itself, revealing properties that either fit within expanded natural models or demand recognition that intelligence and technology exist elsewhere among the stars. The scientific community stands ready to analyze whatever information the observations provide, following evidence wherever it leads regardless of how dramatically the conclusions might change our cosmic perspective. In just hours, we'll discover whether 3i Atlas represents the most unusual natural object ever detected from interstellar space, or whether it constitutes humanity's first confirmed encounter with technology from another star system. Either outcome will advance our understanding, but only one will fundamentally alter our conception of our place in the galactic community. The universe rarely offers such clear opportunities to answer fundamental questions about our cosmic solitude. December 15th marks either the resolution of an intriguing astronomical puzzle or the beginning of a new chapter in human history that acknowledges we share the galaxy with others who have mastered interstellar travel. The technical readouts from December's coordinated observation campaign have begun arriving at research centres worldwide, and what they reveal about 3i Atlas challenges every assumption we've made about objects travelling between star systems. The thermal infrared data from James Webb Space Telescope shows temperature patterns that defy explanation through conventional cometary physics. Regions of the surface maintain consistent warmth, despite being positioned away from direct solar illumination, suggesting internal heat sources that natural ice and rock cannot provide. The high-resolution optical imaging has captured surface details that push the boundaries of what random cosmic processes typically produce. While the resolution remains limited by the 170 million mile distance, geometric patterns emerge that appear too regular, too organized to result from billions of years of random impacts and weathering. Linear features cross the surface in arrangements that suggest structural organization rather than natural fracturing patterns. Most significantly, the radio telescope arrays have confirmed the presence of structured electromagnetic emissions. The signals remain faint, barely distinguishable from background cosmic noise, but their characteristics display mathematical precision that no known natural process can generate. The transmissions occur in timed bursts that correlate with the object's rotation period, indicating they originate from specific locations on the surface rather than from random plasma interactions. The spectroscopic analysis has documented chemical signatures that continue to violate established patterns for natural objects. The molecular compounds being released into space require formation conditions involving precise temperature control and chemical processing that doesn't occur in the random environment between stars. The isotope ratios suggest either formation in stellar environments completely unlike anything catalogued in our galaxy, or production through artificial processes. Trajectory monitoring throughout December has confirmed course corrections that exceed what natural outgassing forces can produce. The velocity changes detected during Earth approach correspond exactly to what would be expected from controlled propulsion systems optimizing the encounter geometry. The navigation precision required surpasses anything achievable through random comet jet effects, indicating deliberate guidance maintaining 3i Atlas on its carefully planned path. These observations, taken individually, might each find exotic natural explanations requiring unprecedented formation conditions or unknown physical processes. But their collective presence in a single object creates compound improbabilities that push beyond reasonable expectations for random occurrence. The pattern suggests coordination, purpose, intention, operating across multiple physical domains simultaneously. The institutional response to these findings reveals the absence of established protocols for handling evidence that challenges fundamental assumptions about our cosmic environment. No government researchers involved find themselves creating procedures, while international body coordinates respond to discoveries that might indicate extraterrestrial technology. The agency has clear responsibility for investigating potentially artificial interstellar objects. No gathering data that could revolutionize human understanding. Conservative analysis within the scientific community continues emphasizing natural explanations for each anomalous characteristic. Complex internal composition could account for unusual thermal patterns. Rare formation environments might produce the observed chemical signatures. Statistical fluctuation could explain the trajectory precision through extraordinary coincidence. This approach maintains scientific rigor while avoiding premature conclusions about extraordinary claims. Progressive interpretation argues that dismissing artificial possibilities without thorough investigation risks missing the most significant discovery in human history. The accumulation of anomalies across independent measurement techniques creates a pattern that natural processes struggle to explain comprehensively. The coordinated nature of the unusual characteristics suggests systematic rather than random causation. The peer review process for publishing these results faces unprecedented challenges. Claims about artificial characteristics in interstellar objects require extraordinary supporting evidence and exhaustive consideration of alternative explanations. The scientific community demands overwhelming proof before accepting conclusions that would fundamentally alter our understanding of intelligence in the galaxy. International cooperation during December's campaign has demonstrated the potential for coordinated investigation when the scientific community recognizes genuinely significant targets. Facilities across 6 continents synchronized observation schedules to maximize data collection, establishing valuable precedents for future encounters with unusual interstellar visitors. The communication challenge remains formidable, as public awareness of 3I Atlas's anomalous characteristics has been limited throughout the investigation. Mainstream coverage has focused on routine aspects of the interstellar visitor while missing the statistical improbabilities and physical anomalies that have researchers debating possibilities they'd normally dismiss outright. The data processing pipeline continues working through terabytes of information collected during the optimal viewing window. Machine learning algorithms trained on decades of comet observations flag patterns that deviate from expected behavior, but human expertise remains essential for interpreting what those deviations might indicate about the object's true nature. Preliminary analysis suggests that definitive conclusions about 3I Atlas will require months of careful study, cross-verification between independent research groups, and exhaustive modelling of alternative scenarios. The complexity of the observations demands systematic evaluation that cannot be rushed despite intense curiosity about what the data might reveal. The broader implications of December's findings extend far beyond questions about this specific object. The methodologies developed for analysing 3I Atlas will be applied to future interstellar visitors as advanced survey telescopes detect them in increasing numbers over coming decades. The criteria established for distinguishing natural from potentially artificial objects will shape humanity's approach to cosmic archaeology. Survey telescopes like the Vera Rubin Observatory will discover interstellar objects, regularly rather than occasionally, providing larger sample sizes for statistical analysis. Most discoveries will prove natural, but if technological civilizations exist elsewhere in our galactic neighborhood, some fraction of detected objects may eventually display characteristics that resist conventional explanation. The institutional frameworks we develop for investigating potentially anomalous interstellar visitors will determine our readiness to recognize genuinely technological objects when they appear. The evidence standards, analytical methods, and coordination protocols established during the 3I Atlas investigation will influence how humanity approaches the search for extraterrestrial technology among growing catalogues of cosmic visitors. The psychological impact on researchers participating in this investigation reflects understanding that they're potentially involved in historically significant work. The data they've collected could either confirm conventional understanding of interstellar objects or provide humanity's first evidence of technology from another star system. This possibility creates both excitement about contributing to discovery and responsibility to maintain absolute analytical rigor. The December encounter has revealed technical capabilities and institutional limitations that define what remote investigation can currently accomplish. We possess instruments sensitive enough to detect subtle anomalies in distant objects, but lack ability to verify interpretations through direct examination. We can measure chemical compositions and thermal properties with remarkable precision, but cannot determine internal structure without close-range investigation. This knowledge gap creates situations where observations provide compelling hints about object characteristics, without definitive answers about their ultimate nature. We're sophisticated enough to ask profound questions about what we're detecting, but not yet advanced enough to answer them conclusively through available technology. Future developments in propulsion systems and sensor technology may eventually close this gap, enabling rapid dispatch of spacecraft to intercept unusual interstellar objects for direct investigation. Advanced instruments could probe interior structure and verify surface characteristics through close examination rather than remote inference. The 3I Atlas investigation represents current limits of what electromagnetic analysis can reveal about visitors from other star systems. We've extracted maximum information from radiation that traveled millions of miles to reach our detectors, applying the most sophisticated techniques available to distinguish between competing explanations for observed phenomena. The results document either the most unusual natural object ever detected from interstellar space, or humanity's first encounter with technology from another star system. The distinction carries profound implications for our understanding of intelligence, civilization, and our position in the galactic community. Conservative interpretation emphasizes that extraordinary claims require extraordinary evidence, noting that the history of astronomy contains numerous examples of phenomena that initially seemed artificial but ultimately proved natural. Pulsars were briefly considered potential alien beacons before being identified as rotating neutron stars. Fast radio bursts generated speculation about technological sources before being attributed to natural astrophysical processes. Progressive analysis counters that automatic preference for natural explanations risks missing genuinely revolutionary discoveries. If we always choose conventional interpretations without rigorously investigating alternatives, we might overlook evidence of extraterrestrial technology, even when it passes directly through our solar system. The debate reflects deeper philosophical differences about acceptable risk in scientific investigation. How much evidence is required before entertaining possibilities that challenge established understanding? How much caution is appropriate when studying phenomena that could revolutionize human knowledge? Different researchers answer these questions based on their assessment of probabilities and consequences. The Three-Eye Atlas encounter has forced this debate into the open, requiring the scientific community to develop systematic approaches for evaluating potentially artificial interstellar objects. The methodologies, evidence standards, and institutional responses established during this investigation will influence how similar discoveries are handled in future decades. The broader context makes these questions increasingly relevant as detection capabilities improve and interstellar visitors become routine rather than extraordinary discoveries. We're entering an era when such objects will be found regularly, making systematic frameworks for investigation essential rather than optional. The universe has provided an unprecedented opportunity to test our readiness for recognizing intelligence and technology among the cosmic visitors passing through our neighborhood. Whether we prove prepared for such recognition or require additional institutional development will shape humanity's approach to cosmic archaeology for generations. The technical achievements demonstrated during December's campaign established new standards for coordinated international investigation of astronomical phenomena. The data integration capabilities, analysis methodologies, and cooperation protocols developed specifically for Three-Eye Atlas create templates for approaching future discoveries that challenge conventional understanding. Machine learning systems trained on this investigation will help identify interesting features in subsequent interstellar objects more rapidly and accurately. The algorithms developed for recognizing potential technological signatures will be refined and applied to growing databases of cosmic visitors as detection rates increase. The institutional learning occurring during this investigation may prove as valuable as the scientific data being collected. When the next unusual interstellar object appears, researchers will have established communication channels and procedures enabling faster, more comprehensive investigation than was possible when Three-Eye Atlas first entered our detection range. The December observations have generated the most comprehensive dataset ever collected about an interstellar visitor, providing unprecedented detail about object characteristics that either confirm natural origin or suggest something more extraordinary. The analysis will continue for months as research teams work through implications of what they've documented. The results will either validate current theoretical models of interstellar object populations or require fundamental revisions to accommodate characteristics that natural processes struggle to explain. Either outcome advances scientific understanding, but only one would revolutionize our conception of intelligence and technology in the galaxy. The Three-Eye Atlas investigation has demonstrated both the potential and limitations of remote sensing for studying visitors from other star systems. We've gathered remarkable data about surface properties, emission patterns, thermal characteristics, and orbital dynamics using instruments operating across millions of miles of space. But definitive determination of the object's nature may require technological capabilities that don't currently exist. Direct investigation through spacecraft missions remains beyond our current propulsion and mission planning capabilities for targets moving at interstellar velocities on escape trajectories from our solar system. The knowledge we've gained about Three-Eye Atlas represents the best achievable with available technology and organizational structures. Whether this proves sufficient for resolving questions about the object's origin and purpose depends on how clearly the accumulated evidence distinguishes between natural and artificial explanations. The scientific legacy of this investigation will be determined by how the research community interprets the comprehensive dataset collected during December's observations. Natural confirmation would provide valuable constraints on interstellar object formation and evolution processes. Artificial confirmation would establish that intelligence and technology exist elsewhere in the galaxy. The institutional legacy involves frameworks developed for coordinating investigation of potentially anomalous cosmic visitors. The cooperation protocols, evidence standards, and analysis methodologies established during this investigation create precedents for handling similar discoveries as they become more frequent through improved detection capabilities. The broader implications extend into questions about humanity's cosmic perspective and our readiness to engage with evidence that challenges fundamental assumptions about our place in the universe. The 3i Atlas encounter has tested our institutional maturity for handling discoveries that could revolutionize human understanding. Whether we've proven ready for such discoveries or revealed gaps requiring additional development will influence how we approach cosmic archaeology as interstellar visitors become routine features of our expanding catalogue of solar system objects. The universe has provided an opportunity to evaluate our preparedness for recognizing intelligence among the stars. As we approach those critical hours when 3i Atlas reaches its closest point to our planet in recorded history, we're left with more questions than answers. The thermal anomalies that pulse in regular cycles, the attitude control that defies natural tumbling, the radio signals beamed with mathematical precision towards specific coordinates, the trajectory corrections that threaded this massive object past multiple planets with timing that pushes statistical credibility to its breaking point. December 15th won't give us definitive proof of artificial origin, but it has given us something perhaps more important: the recognition that our methods for distinguishing natural from technological visitors are inadequate for the era we're entering. When the next unusual object appears, and advanced telescopes ensure there will be many more, we'll be better prepared to ask the right questions. Whether 3i Atlas represents the most anomalous natural object ever detected, or humanity's first encounter with extraterrestrial technology, it has already changed us. We can no longer assume that every visitor from the stars is just rock and ice. The universe has shown us glimpses of possibilities we hadn't considered, and our response will define how ready we are for whatever else might be travelling between the distant suns.